Welcome to the full course of Becoming AI Researcher. I will guide you step by step through mathematics and then PyTorch fundamentals, neural networks, and lastly, transformers. After finishing this course, you will have all of the fundamental knowledge necessary to start doing your own AI research, to start understanding others' AI research and publishing your own papers. First, we will start from basics, talking about functions in mathematics, different types of functions, and what each term in a function determines. Then we will talk about derivatives, how derivatives show a rate of change of a function and how they are used later in neural networks. After that, we will learn about vectors. Vectors are present everywhere in large language models, reinforcement learning, robotics, and neural networks, and anywhere else you can imagine pretty much. They are used for everything. Then we will combine our knowledge of vectors and derivatives to figure out gradients. Gradients are used for learning of the neural network. Gradients is how neural networks learn. So you will understand what they are, how they show the direction of steepest ascent, how to use them to make neural network errors lower, how to use them to make neural networks learn. And by the way, right now I'm also explaining to you your roadmap, your path to become AI researcher, what you need to learn. So keep track of what I'm explaining. This is not just an intro. This is your roadmap to becoming AI researcher. So you can self-study as well. Next are matrices and matrix multiplications. These are maybe the core of neural networks besides gradients. They are done on GPUs. Neural networks are all about calculating matrices and doing it quickly and efficiently. And lastly, in the math module, we have probability. This is used also absolutely everywhere. Neural networks, large language models, reinforcement learning, robotics, everywhere. Video generation, diffusion, image generation. Then there is PyTorch module. The first lesson includes creating tensors, understanding data types. Then matrix multiplication, different operators and how matrix multiplication works in PyTorch. Then transposing, flattening, reshaping, viewing, squeezing, unsqueezing tensors. All of these things are gonna be used very frequently in AI research, so you need to understand and master them. And I have a lot of examples for you to play around. You can find this GitHub repository below the video, the first link in the description. You will also learn tensor indexing and slicing. So if I tell you I want last two rows, and out of those last two rows, I want second to fifth columns. And so you need to be able to quickly write indexing logic. Then we will talk about special matrices and arrays like identity matrix, random matrix, lin space, etc. After PyTorch module, we will work with neural networks. First, we will create a single neuron, understand what weights and biases are, how they influence the output, how they are calculated. Then activation functions, how they turn the straight line of weights and bias and input multiplication into a curved line that can encircle data. We will talk about different activation functions and what they are useful for. We will also talk about multi-layer neural networks and how to have entire layer of weights in a single matrix and how that matrix multiplies inputs and how the results get transformed. So we will be building neural network layers from scratch, coding it step by step with all of the functions explained step by step in this course, as well as backpropagation and how neural networks learn. And finally, in the last module, we will talk about transformers. Transformers are a base of today's large language models, as well as image generation, video generation, audio generation, and almost everything. You will understand the attention mechanism, and then on top of that, self-attention and multi-head attention, and then the feed-forward networks and layers of the transformer and how all of that works, as well as tokenization. And this will be a good base for building your own large language model, as well as video generation, image generation, and other models. So that's the roadmap that we will follow. You can also follow this roadmap by searching other YouTube videos and self-studying. And if you are ready, we will begin. Thank you Beam AI for sponsoring this video. You can automate your business processes and operations without any technical skill or coding required. Here I can just go onto this chat and say create custom agent with Beam AI, And then I can just type, create me an AI agent for order processing. This can be email forwarding, data processing, data entry, Google Sheets, whatever you need in your operations. There is no coding or technical skill required. You can just write in natural language like you are talking to a coworker, and it will automatically generate the workflow for you. It's gonna understand your intent, then prepare your agent, generate prompts, generate tools, connect external tools, APIs, etc. So here it gives me this suggestion. I can give feedback or just click create. And then I will just continue talking in natural language. I need you to validate order against inventory. And it will give you whole suggestion of the workflow, step 1, step 2, step 3, everything. And then you can adjust, or you can just say this looks good and create this workflow. And you see that automatically created entire workflow with all of the tools automatically generated, and you can adjust all of them very easily. Everything from emails, customer support, HR onboarding, finance, refunds, order fulfillment, and a lot more can be automated with just simple natural language descriptions without you needing to do prompts, building complex workflows, or caring about connecting external APIs. Everything is done automatically by Beam. You don't need any coding or technical skills. You can just explain to it in natural language like you are explaining to a coworker. You want it to generate invoice, process invoice, forward email, sort messages, extract some data, etc. Here is an example of how easy it is to use Beam AI. So let's say I got an email in my previous node, previous step. Then I'm gonna just click this plus button and insert a step. And then I'm gonna say extract competitor data from email. And then I'm gonna click add tool and generate tool. And it will use my text here that I wrote. And then it's gonna generate entire prompt. It's gonna be very detailed and professionally done, as if an expert prompt engineer is writing this. So you can just click here a few times and forget about it. It will automatically do everything. And just after 1 to 2 minutes, it generated this whole new tool with very professionally designed prompt and the fields it's going to extract. And this data can be easily used in the following notes you add to save it to Google Sheets, etc. Click the first link in the description or go to beam.ai to request access and start automating. Hello guys, this is Mathematics for AI Research. If you understand and learn the math I'm gonna explain in this video, you will be able to take any AI research paper and understand math within it as well. And you will be able to continue doing research in any part of AI that you wish. So is it large language models, transformers, video generation, diffusion, image generation, reinforcement learning, robotics, whichever part of AI you are interested in, this is fundamental math that appears in everywhere. This is gonna be part of my course on creating and training large language model like Kimi K2 thinking from scratch, but this math applies to the entire field. Whichever AI research you are doing, you're gonna have to be learning this math as well. If you click the first link below this video, you're gonna get to this repository, Become Elite AI Researcher, and the first module is math, which is what I'm gonna explain now. We have all of these Jupyter notebooks. So requirements here is that you understand basic Python. So here we have some array, we have some for loop, we have some variables. So this is all basic Python. So if you are not familiar with basic Python, you can just type a Python tutorial on YouTube and you can check whichever one you like. Maybe this one, or actually Harvard classes are actually very good. So I want you to know how to execute Python code. It can be on your local machine or it can be in Google Colab. So now I also want you to say Google Colab tutorial if you want to use Google Colab, but also you can just run it on your local machine. So whichever one you prefer. Also, if you're using VS Code or Cursor or some fork of VS Code, you can install this brand new Google Colab extension. So if you just search for Colab, it's by Google, install it, and then you can connect to Google Colab GPU, CPU, TPU from your local environment, from your local Jupyter notebook. So now on my GitHub repository, in the math folder, I want you to open this first Jupyter notebook. So you can copy this and open it in Google Colab. As I explained, you can ask ChatGPT how to do it, or open it in your local, or however you want to open this. And then I have it here on my local, and we're gonna go through this. So if you install Google Colab extension, you can click here Google Colab, and we can say open Google Colab web. But I don't want to open this on web. I want to say select kernel with which to activate this, and select another kernel, and then Colab. And then I can create new Colab server, and then I can choose CPU in this case, because I don't need to run this on GPU. But keep in mind, now you can write a name. I can just use the default name like this, press enter. But you don't actually need to do this if you want to run the Python code on your local computer. So I'm showing you how to run it from your local using Google Colab, Google's GPUs or CPUs. But you can just run it locally as well. And so if I click here Colab, I can click remove server if I want to shut down the server. But anyways, first, depending on which kernel you are running here, if it's Google Colab, it will have these NumPy, Matplotlib already pre-installed. But you may also want to create your own environment. And this is something you would learn how to do on YouTube or from ChatGPT, and you need to install these requirements. So if you try to run this, but you get error like NumPy or NP is not defined, then you don't have these requirements installed. So make sure you enter your console and make sure you are in the folder where in which the requirements are. So this is the outside folder in which requirements file is. And then I'm gonna say pip install -r requirements.txt, but make sure to create your environment. Install this in a Python environment, and then just press this, enter. But actually, I don't want to install PyTorch, because for the PyTorch tutorials, I'm gonna use Google Colab. So I'm just gonna install NumPy and Matplotlib, and then I'm gonna comment out PyTorch. So let me do the installation again. Okay, now this is already installed. So let's start with the maths. Now that you have everything set up, everything installed, I will show you the curriculum. First, we're gonna learn the functions. So these are math functions, not Python functions, but math functions. Then derivatives, then vectors, gradients, matrices, and probability. A lot of you may already be familiar with some of these, especially maybe with functions. But you can use timestamps below or chapters to skip, but maybe you can also watch it anyways. So function will map from one value or from one set of values, but let's make it simple. You have some value x equals 1, your function will transform it into some other y, like y equals 2, based on some rules. For example, if we have function that y is equal 2 times x, then if x is 1, y will be 2. If x is 5, y will be 2 times 5 is 10. And I want to draw this so as x goes 0, 1, 2, 3, 4, the y is going to be the double. So here, for example, at 5, y will be 10. So then for every x, we're going to take and draw corresponding y. So for example, for 2.5 right here, y will be 5. For 2, y will be 4 right here. For 5, y will be 10. So if we then just connect all of these dots, we draw all of these dots, we get this line. So this is a linear function. And this is how we drew. This is where the plot drawing happens. So you don't need to understand this part at all. This is just to show this plot. So let's just understand this part. This is our function. So we will create an array of x values between 0 and 10. And we're going to create 100 x values between 0 and 10, which is including 0 and 10. So you see we have x from 0 to 10, and in between we have 100 small dots. And for each of these, we're gonna just calculate the y corresponding y values. So 2 times these x values. So y will also be an array of 100 numbers, but each element will be 2 times the corresponding element in the x. So if it's 3, it's gonna be 6 here. 4 will be 8, etc. And then we just use this to draw. And that's how we draw the linear function here. And let's see if instead of having number 2 here, we have some other numbers. So y is equal to 1x, 2x, 3x, 0.5x, minus 1x. So this number will determine the slope of this linear function. The 3x, which is the highest number here, will also have the highest slope. The lowest number, minus 1, will have kinda highest negative slope in negative direction on negative x. For example, if we look at y equals x, here where x is 4, y will also be 4. So then that's this slope as well. And the way this is coded is very simple. There is a list of k values, and then we just plot for each of the k values, we plot the function. I recommend using AI, ChatGPT or Cursor to explain any of these things for you if you don't understand it. But I want to focus on the theoretical part of the math for now. So this coefficient determines the slope of the function. Then there is quadratic function where y is equal to x squared. So as we go on x slowly, the y will become a lot bigger, will start to accelerate. So in the beginning, y doesn't grow so quickly, but later, when we go from 2 squared, 3 squared, 4 squared, 5 squared, the y starts to become a lot bigger, a lot faster. Here, like 0 squared is 0, 1 squared is 1, 2 squared, 4, 3 squared, 9, 4 squared, 16, so y starts to grow very fast. You can play around with this code to see and to modify it to see what the drawing will look like. Now notice that y is always positive here, so y never goes down below 0 on y-axis. We never go down because square function, quadratic function, will always make everything positive, because if you multiply two negative numbers or negative number with itself, it's going to become a positive number. So if you square a negative number like minus 2 here, it will become a positive number. But that's not true for the cubic function, where putting a negative number cubed will give you negative number. So this is what cubic function looks like, and it grows even faster than square function. Here at 3 we are already at 27 on y, and 3 was just 9 in the square here. So cubic grows even faster, but there is also negative part of it. So this is the shape of the cubic function. This is the shape of the square function. So knowing these shapes is good. Square root function. So y is equal to square root of x. I'm gonna have the same code here, so I put some numbers. You can only find roots of positive numbers, by the way. You cannot find roots of negative numbers. It's not defined, or it's not real, I should say. And so this is what y equals square root of x looks like. This is also good to know, this kind of function. It's growing very fast in the beginning, but then it's starting to grow slower and slower. Although this will grow to infinity as well. So there is no limit here. It will also grow forever. As x grows forever, y will also grow forever. Then we have exponential function, where y is equal to 2 power x, or some number, some constant power x. And this grows very fast. This grows faster than the quadratic. So 2 power x grows faster than x power 2. it's good to know that. And this is the shape of exponential function. The code is very similar. This part is just different. So y is equal to 2 power x. This is how you can denote power in Jupyter or Python. We also have sine functions. So y is equal to sine x. And I'll show you first that this is a periodic function. And this function is important. It's a trigonometric function. It's used everywhere. It's used so often. And in Python, you can just write y is equal to math.sine of x. Now let's go back to the linear function. So this is also a linear function. So we have some 2 times x, which is coefficient and the variable, plus some constant or minus some constant that doesn't have times x in it. Or so if you change this number 3, make it 4, 5, 6, you will just move this function left or right. So the slope will be same. So if you change this number 2, then you will change the slope of the function. But if you change this number 3, you will just move it left or right. This is also important to know. And now we may take a look at these functions. And so that's going to be math functions. I recommend you play with this, make sure you understand this, and we can go on to the next lesson. Next we have derivatives. I'm going to try to explain the main points of derivatives. So if you have a function, you can find the derivative of that function that shows the rate of change of the function, how quickly it grows at each point. So you see, this linear function is always growing at the same rate. So this function is not like quadratic where it's growing a bit slower here, a bit faster here, etc. This linear function is always growing at the same rate. In this case, the derivative is going to be equal to this number 2. So if we have 2x, the way I'll show you later how to calculate derivatives, but the derivative will be this 2. So at any point, when you increase x by a little bit, when you go in the x forward by a little bit, the y will go by 2 times that amount you went on x. So you move x a little bit, the y will go up by 2 times. So here you can see the derivative is 2 at any x. So at any x here the derivative is always 2. Because it's a linear function, the growth is always the same. Can you try to explain yourself what derivative is? Can you try to explain what I just explained yourself? So derivative shows rate of change. And it's linear function, so rate of change is always the same. And it's 2 in this case. It's equal to this number 2 of 2x. So in my code, I have the function f of x. And the derivative is just hard-coded here. It's always 2. Because I'll show you later how to calculate it, but this will be derivative 2. Let's see derivative of this quadratic function y is equal x squared. So the derivative here will be 2x. And I'm going to explain how it's calculated, but we can see that here the function doesn't grow equally everywhere. So actually as we increase or go further into negative on x, the y will start growing a lot faster. Here around 0, x is growing, but y is not growing up so much. But as we grow x, the y grows a lot faster. So now we don't have a constant derivative that's always the same, like 2, the constant growth. Here we have derivative looks like a linear function. So the derivative here is 2x. So the derivative itself can be drawn as a function, by the way. So we have 1 and 2 for this spot. So funnily enough, you can also take derivative of this derivative. So that would be second derivative. So here the growth will be just 2. Derivative of 2x will be just 2. But let's not get confused. So here we have the function x squared. The derivative is 2x. Because the formula is you put this. So if you have x to n, you put this number 2, number n in front of x. So you get 2x. You just put this number in front of x, so you get 2x, and you subtract 1 from this number up here. So 2 minus 1 will be 1, so you will have x to power 1, so that's just x. So the derivative of this is 2 times x power 1, which is just 2x. That's the formula for calculating derivatives. You can also check other tutorials. Now this can go quite deep. I think it would be good if you knew it, but it's not absolutely essential to master this. I'm just explaining. These are the things you need to understand. You also learn this in high school. So you will encounter this in some research papers, and it's good to know this stuff. Now, do you want to dive deeper right now or later? It's up to you. So what this derivative means is that any of these points, wherever you pick x, for example, if you look at x equals 2, then that means here on this original function, if at x2 you increase x by just a little bit, then the y will increase by 4. You see here it's number 4. So if you increase x by a bit, the y will increase 4 times, because at this particular place, let's calculate derivative. Derivative is 2 times x, so 2 times 2 is 4. So at this particular place, if you increase x by a little bit, the y will increase 4 times that little bit of your increase. Here, at 3, derivative is 6. So at 3, if you increase x by a little bit, the y will increase 6 times that little bit. And so you can see that y is increasing faster and faster as you increase x. So this may require a bit of practice, a bit of maybe pen and paper. You can try to think about this yourself. Maybe watch some specific tutorials on derivation if you wish so now, or maybe even later. So we have this quadratic function, and I want to show you at each of these points, whichever points we pick, 0, 1, 2, on the x-axis, each point has its slope. So because it's quadratic function, we can see that there is no slope at 0. X equals 0, there is no slope because y is 0, x is 0 here. At 1, there is a slope. At x equals 2, there is even higher slope. So this slope is basically the derivative. I told you that at x equals 2, if you increase x by a little bit, by 0.001, for example, the y will increase by 4 times that amount. Now, I'm not going to tell you that if you increase here x by 1, so you go from 2 to 3, the y will increase by 4, because I'm not going to tell you that, because as you move towards 3, the y rate of change will also be increasing. Keep in mind that the slope will change. That's why I say if you increase, so just around this 2, a little bit around this number 2, the slope is 4, okay? As you move towards 3, the slope will become 6, it will increase. So that's why I say if you just increase x by a little bit here, the slope will increase by this amount, 4 times or 6 times. But if you increase x by a bit, by a lot more, then the slope will also change. So in summary, the derivative will show you this slope. It will show you rate of change around this point. And for this particular function, the slope or the derivative will be equal to 2x. So here, if x is 1, the slope is 2. If x is 2, slope is 4. If x is 3, slope is 6, etc. Now let's see some derivation rules. So if you have x power 3, you're gonna put this 3 in front of the x, so the derivative will be 3 times x, and also you need to subtract 1 from this exponent. So 3 minus 1 is 2, so the final derivative will be 3 times x power 2, and it's just x power 2, so it's x power 2 times 3. And so you can see these examples like derivative of x power 5 is gonna be 5 times x power 4. You just subtract 1 here, so it's x power 4 times 5. And this 4 is not like, it's not the whole thing, it's just x power 4. And so if we have a function y equals x cubed or x power 3, then the derivative will be 3x squared, according to the rules. So this is the derivative function, it's 3 times x squared. And so we already know that x squared is gonna be like this U shape. We discussed that earlier. And then 3 times x squared, so it will just make the y's even larger. It will maybe squish it like, so this coefficient will just change this, how wide or thin the U shape is. But basically, because we have x squared, we're gonna have U shape. So that's the derivative. It shows how the function is changing at any of these points. Some other derivation rule. So if you have a function 2x plus 3, you can find derivatives of each of these separately. So around plus or minus. So you can find derivatives of 2x and derivative of constant 3. And the rule is that constant 3, any constant, becomes 0. So it will just be plus 0. So we can omit that. And derivative of 2x will be, so the rule is the following. If you have constant times variable, the constant will remain the same. So 2 will remain the same because it's times variable, okay? Here, this constant 2 is not separate. So here, 3 doesn't have any variable attached to it. 3 is not multiplying a variable, so 3 disappears, it becomes 0. But here, constant 2 is multiplying a variable, so it remains 2. In the derivative, this constant 2 will remain 2. It's explained well in ChatGPT. So as I said, derivative of a constant, it's a lone constant that doesn't multiply variable. Like here, 2, constant 2 multiplies variable. So this is not a lone constant. So if you have a lone constant doesn't multiply variable, then derivative is 0. So this part will be completely deleted, omitted. And then derivative of 2x is 2. Let's see how. So 2x is equal to 2 times x power 1. And we know that I explained earlier that if we find derivative, so first of all, because we have constant times variable, we will just, this constant will remain the same. So in the derivative, this constant will not change. So in the derivative, this will still be 2 times something, okay? So now let's see what that something is. I told you the rule is, whatever power you have here, you put it in front of the x. So 1 will go in front of the x, and then you will subtract 1 from whatever power we have here. So we have 1 minus 1. So 1 times 1 minus 1. So that's 1 times x to 0. X to 0 is just 1. So this is equal to 1. Any number to 0 is equal to 1. So that's going to be 1. Okay? So then I told you, we will just get 2 times 1 because, as I said, 2 multiplies variable, so it remains the same in the derivative. And then we apply this rule x to the x that I explained, so it will be just 2 times 1. And so this derivative of 2x is 2. So at the end, derivative of this is 2, derivative of this is 0, so we get 2 plus 0. We get derivative of this whole thing is 2. So you can practice this. This is done in high school, university. You can practice this yourself if you want with ChatGPT or some other AI or YouTube videos. And I can show it to you here. So the function is 2x plus 3. The derivative is 2. It's always 2 for any x. Whenever you increase x, the y will increase by 2 times whatever the increase in x was in this function, because the derivative here is always 2. So this means that plus 3 constant doesn't affect the slope of the function. As I said, the slope is determined by this number 2. And so if I change this number 2, the slope of the function will change. But this constant plus 3, this will just move the function left or right. So this constant plus 3 will not change the slope. So it makes sense that it disappears in the derivative as well. It becomes 0. It doesn't affect the slope. And now I just want to summarize derivative. So we have linear function, the derivative is constant. We have quadratic functions, so x power 2, the derivative is linear, so x power 1 is the derivative. We have a cubic function, x power 3, the derivative will be x power 2, it will be quadratic. So the derivative is kind of 1 degree less than the function. So that's going to be the core knowledge you need to know about derivation. You will eventually learn more as you read papers, but for now this is enough. Third lesson, let's learn about vectors. So this is maybe the most important one besides matrices as well. Everything is in vectors in machine learning, in neural networks. First, we will look at a vector as just an array of numbers. So here we're going to create a NumPy array. Hopefully you understand what NumPy is. You can watch YouTube if you don't understand this Python. So these are fundamentals. You can learn that first. So array of just two numbers in this case, 3 and 4. Vector can be array of any amount of numbers. And we can also look at these numbers as coordinates on a coordinate system. So x is 3, y is 4. We can look at that this way if we want. So this blue example, it's gonna be x is 3, here 3, and y is 4. So that's the vector, the spot. So we can draw a vector by going from 0 to that spot. And you can see that vector is like an arrow. So vector has a direction and length. Direction and length. We can also look at a vector as going like 3 units this way and then 4 units this way to end up at this spot. And here we have two other examples of minus 2, 1. So going minus 2 on x and 1 on y. Minus 2, 1. And 0, 5. So 0 on x, 5 on y. So this vector will be on the on the y-axis. Then let's look at vector addition. So if you have vector 3, 2 and vector 1, 3, if you add them, you're gonna say you add the first elements. So you add 3 plus 1, the first elements will be 4, and the second elements, 2 plus 3, will be 5. And we can also add vectors visually, starting from the first vector 3, 2, going from 0 to 3, 2, and the second vector 1, 3. Now this vector would go here from 0, 0 to 1, 3 like this here. So this would be this second vector. And then we will just move this second vector to the end of this first vector if we want to add it visually. And so wherever it ends up, that's going to be our resulting vector. So the resulting vector will be 4, 5. We can draw it from origin to 4, 5 if we want. So that's how you can add vectors visually as well. Let's see multiplying vector with a scalar. So if we have vector 2, 1, what happens if we say 2 times that vector, 0.5 times that vector, minus 1 times that vector? So this blue is our original vector. So it goes from 0 to 2, 1. Now multiplying with a scalar will stretch or squish or inverse, so make it go in the other direction. So 2 times vector 2, 1 will give us vector 4, 2. So you multiply each of the elements. So 2 times v is going to be 2 times 2, it's 4, and 2 times 1, it's 2. So the resulting vector will actually be 2 times longer, and it will have same direction. And multiplying with 0.5, it will just make it 2 times shorter instead. Multiplying it with minus 1 will have the same length, just the opposite direction. So it will be minus 2, minus 1. How do we calculate length or magnitude of vector? How long is this vector? So it's actually similar to Pythagoras' theorem. So you can just say x squared plus y squared. You add them up, and then you get the square root of the result. But in Pythagoras' theorem, you just have two numbers. But here you can have any amount of dimensions. So you can have x squared plus y squared plus z squared plus a squared. So you just add all of the squares of every dimension. And at the end, you take the square root of that sum. So let's say we have a vector that has 4 dimensions. Let's say this is the vector. And then we just square each dimension, sum them up. Let's say it's 30, the square of the sum of all the squares. And then take the root of 30, and that's the length, the magnitude of your vector. So it's always the square root. It's not like fourth root here, it's square root always. Here are some examples. If we have vector 1, 1, the magnitude will be 1.41. So that's the length, the magnitude of the vector. So you can see here that this is a bit longer than this 1 unit. So it's about 1.41. Here, the vector 0, 5, the magnitude will be 5 here. You can already see that the length of this is 5. So, okay, and then vector 3, 4, 3, 4, the magnitude, the length of the vector will be 5 units. And if you remember from Pythagoras' theorem, if you have triangle with sides 3, 4, the hypotenuse will be 5. But what's gonna happen often is if you have some vector that has some length, you will want to squish it back so it has unit length of 1. This is to make vectors in neural networks stable. They don't, because you are multiplying a bunch of them, so they're gonna start exploding. The resulting vectors will become exponentially or quadratically or a lot bigger and bigger and bigger as you multiply them, or they will become a lot smaller and smaller and smaller and vanish. So you will want to normalize vectors. You will want to make vectors of unit length, of length 1. Let's say we have a vector 3, 1. You will find its length, which is going to be 3.16 in this case. And you will just divide this vector with its length, with its magnitude. And when you divide, so dividing it means you will divide each dimension with the magnitude separately. And then this new vector is gonna be unit length. So it will have same direction. It will just have unit length. It will not be, it will be long 1 unit, whatever the unit is. So neural networks like numbers around 1 because when you multiply a bunch of those numbers, it will not start to, the result will not become very huge or very small, which is not good for graphic cards. They cannot represent very huge numbers or very small, very big numbers or very small numbers. So you want to keep your numbers around 1, 0, -1, something like that. Now let's understand dot product. So dot product shows you how similar two vectors are. Here on this image, you can see that we have vector A and vector B. And these two vectors are closer together, so which means they are more similar than here, where there is 90-degree angle between them, or here, where they are very separate. So these two vectors are most similar. These are less similar, and these are least similar. Maybe I should say aligned instead of similar, but word similar is also used very frequently, maybe even more frequently. So it's very simple. We will multiply first dimensions. So here we have a vector, let's say 3, 4, and the second vector is 1, 2. To find dot product or similarity between them, we multiply 3 times 1. So we multiply the first dimensions, and then we say plus multiplying second dimensions 4 times 2. Okay, so 3 times 1 is 3 plus 4 times 2 is 8. So 3 plus 8 is 11. So dot product between these two is 11. So if our number is positive, like 11, then they are pointing in the same direction, okay? If the two vectors are perpendicular, 90 degrees angle between them, then the dot product will be 0. Okay, so if you get the dot product 0, you know that these vectors are perpendicular, and this is useful in muon optimizer. This may be the new way to make neural networks learn a lot faster, better. I'm gonna talk about this in a different part of the course. So just know that if vectors are 90 degrees between each other, they will have dot product 0. And if you have dot product 0, that means the vectors are 90 degrees. And if dot product is negative, then the vectors are even further away than 90 degrees between them. So they are even more different or dissimilar. In Python, we can calculate dot product by just calling np dot dot v1, v2, vector 1, vector 2. So vectors v1 and v2 that we calculated manually have dot product of 11. Now these two vectors, 3, 4 and minus 4, 3, have dot product of 0, which means they are perpendicular. So v1 and v3, you can see that the angle between them is 90 degrees. So they are perpendicular, so dot product will be 0. And then v1, v4, so v4 is actually minus 3, minus 4, so the blue and the yellow, they are very different because they point in very different directions, opposite directions. So their dot product will be like negative number, minus 25. It's gonna be large negative number here because they are very different. Subtracting vectors is very easy. If you have vector 4, 3, you wanna subtract vector 1, 2, you will just subtract each element from each. So 4 minus 1, that's gonna be your first element, which is gonna be now 3. And the second element will be a result of 3 minus 2, which is gonna be now 1. So the new resulting vector is 3, 1. We can also show that visually. So if we have this blue vector, which is 4, 3, and we have a red vector, which is 1, 2, we can draw a vector from the end of this one to the end of the first one, and then move it back to the origin. And that's gonna be our new vector, which is gonna be 3, 1, our resulting vector. So you will start from the second vector that you are subtracting, going to the end of first vector from which you are subtracting. That's your new vector. So then you can move it to the origin to see its real coordinates. And that will be it for vectors, and see you in the next lesson. Let's talk about gradients. Let's say we have some surface like this. So at any point of this surface, you would want to know in which direction to move to go up, in which direction to move to go down. This is used in neural networks to know if, for example, this surface would show error. So you want to make error small. So you want to go down on this surface. So how do you, in which direction to move to go down on this surface? Now I know if you've never heard of loss function and in neural networks, then this is confusing, like how is this showing an error? But we will talk about this later. But just know that if you have some surface, you're gonna use gradients to know which way is you need to move to go up, which way you need to move to go down. Because the gradient will show you the direction of the steepest ascent. So in this direction, if you want to go up fastest. So that means that in the opposite direction, you're gonna go down fastest. For this point where you are standing, so very near around that point. So that's what gradients are used for. For every point on the surface, they show you in which direction it's ascending, increasing. And so in neural network, we will just go in the opposite direction to decrease because a neural network, it will be used to represent, this surface will be used to represent our error, which we want to minimize the error. And gradients are closely related to derivatives. You know that derivatives are showing you the slope. So in gradients, you will also use derivatives to see the slope, but we will use partial derivatives. So let's see what those are. In this case, we have a 2D surface, so 2 dimensions. We have x dimension and y dimension. And we want to take partial derivative with respect to x and partial derivative with respect to y. So what does that mean? So if we stand at any point, if we just move, let's say, on x direction, positive x direction, we increase x 1, 2, 3, 4. Do we go up or down on this surface? So we want to examine if we move on x. So when we change x, do we go up or down? Are we ascending or descending? So that's going to depend on where we stand at the surface. So we will take partial derivative of this function, this loss function or this surface with respect to x at that particular, so we will know, so when we plug in our particular x coordinate in which we are currently standing into that partial derivative with respect to x, we will know if, for example, when we increase x, if the function will increase or decrease. So that's the partial derivative with respect to x. And it's partial because there is also y. So we have 2 partial derivatives with respect to x and with respect to y. So then for that same position where we calculate if we increase x, does the loss increase or decrease? We will also calculate for y. If we increase y, does the loss increase or decrease? So if we find that as we increase y coordinate, the loss will increase, then we want to go in the opposite direction. We want to move in the y decreasing direction. So if, let's say, this is y increasing, we want to move in the y decreasing, so the loss will also decrease as we move. So that's in the case if we find that partial derivative with respect to y is such that when we increase y, the loss is increasing, okay? And it works the other way around. If we find that if we increase y, the loss is decreasing, then we just want to keep moving in that y direction. And so the x direction and the y direction will give us, well, the gradient at that spot will show us the direction of the steepest ascent, steepest increase. So we will just go in the direction of the steepest decrease, the opposite direction. So these are gradients. We're going to see some examples to learn more about this. You can also check some YouTube videos. This may take some time, a few iterations, a few times of you understanding this to finally grasp it. Gradient will just be an array of numbers. And the first number in this array will be partial derivative of the function with respect to x. So it's just a derivative. So if we increase x, what's the change in the function? What's the slope? So it can be 1, 2, 3, minus 1, minus 2, or minus 1.5, or whatever the number is. So we have a derivative of the function with respect to x and derivative of the function with respect to y. And I should say partial derivative. So that's the gradient. So if we have a function x squared plus y squared, here these arrows will show you the direction in which it's increasing most from that particular point where you are standing. So x squared plus y squared will look like this. It will look like a ball, And so here at the bottom, there will not be too much of a slope. So these arrows will be small. The magnitude, the length will be small because there is not too much slope. But as you go to the sides, the slope will be higher, larger. And so the magnitude, so each of these vectors will show you how steep it is. And it will also show you the direction in which it's steep. The longer the vector, the longer the gradient, the steeper it is. And it shows you direction in which it's steep. So if you want to move down, then you would go in the opposite direction of this arrow. If you are standing at this place, you want to go down, you want to go opposite. This is why it's called gradient descent in neural networks. You want to go opposite of the gradient. Because gradient shows steepest ascent, you want to go down the loss function. This is what x squared plus y squared looks like. It's like a ball. Now let's see how to calculate gradient of a simple linear function, 2x plus 3y. We have two variables. So first, in our gradient, the first element will be partial derivative of x with respect to the function. So we will treat y as a constant. If you remember in derivatives, when we treat y as a constant, then this whole thing will be a constant, so it will become 0. It doesn't multiply x, because right now partial derivative with respect to x will just treat x as the variable. So now we will just have 2x as the derivative of this. Oh, sorry, 2 as the derivative of this. And then when we do partial derivative of the function with respect to y, then we just treat y as the variable and x as a constant. So we have 2x, that's a constant. That whole thing is a constant, it becomes 0. So derivative of 3y will just become 3. So here we have partial derivative of a function with respect to x is going to be 2, and partial derivative of the function with respect to y is going to be 3. So it's just gradients and derivatives. In this case, we don't have any variables in the gradient, so we just have constant 2 and 3, which means for this function, the gradients will always be same. It doesn't depend on x or y. The gradient is always the same. So these arrows are always going to be the same. This function will always rise in this way. It's like a plane. It's always the same. Always rising in this way for the same amount is like a plane. But if we have maybe a curvy surface like this, so this surface is x squared plus y squared, we will notice that at the bottom it's a bit flat, so there is no so much rising or ascending or ascent. So the vectors, gradient vectors, will be smaller, but as we go up, these values will grow quadratically, they will grow faster and faster. So as we increase x and y values, the slope will be bigger and bigger and bigger. So these gradient arrows will become larger and larger. As I said, the gradient will show the direction of steepest ascent. So if we have this function x squared plus y squared, if we find first of all the gradient, there is going to be 2x comma 2y. So gradient partial derivative with respect to x will be 2x, partial derivative with respect to y will be 2y. So our gradient for this function will be 2x comma 2y. I can show you here. The function is x squared plus y squared. This is how you can write square in Python. The gradient will be just 2x and 2y. So for, let's see some point like 0.21, so x is 2, y is 1. We're going to get 2 times x is 4, 2 times y is 2, 2 times 1 is 2. So our gradient at 0.21 will be 4,2. 4,2 will be our arrow right here, but it's not shown fully. But anyways, it points to the steepest ascent, so we want to take the opposite arrow to point it at the descent, how to go down the function. Now let's learn about matrices. This is extremely important. This is how neural networks work. This is the main thing about AI neural networks. So this is a matrix. It's an array of arrays. Okay, so you can look at this first row as one array. So 1, 2. This is the one array. And then the second array is 3, 5. So that's one matrix. So each of these numbers has its index. So starting from 0. So this is the 0th row. So the first row is actually has index 0, just like in normal programming. This is a row with index 1, okay? Column with index 0, column in index 1. And so this element has index 0, 0. And then this has 0, 1, 1, 0, because this is a row. So first it's row 1, and then column 0. So 1, 0, and then 1, 1. So if you want to add two matrices, you just add each element, corresponding elements at the same index. So 1 plus 2 is 3, 2 plus 5 is 7, etc. This is how addition works. Matrix multiplication is the most important operation in neural networks, in machine learning, in AI. So you have two matrices. First of all, this number of columns here, 3, must be same as the number of rows here, 3. So this 3 and this 3 must be same. So we have 1, 2, 3 columns, 1, 2, 3 rows. If you swap these places, you will get a completely different resulting matrix. So you cannot swap places of matrices and get same result. You will not. That's a different operation. This is how you multiply two matrices. So you do a dot product between this row and this column, and they must be same length. So 3 times 0 plus 1 times 2, this is the classic dot product, we talked about this earlier in the video, plus 0 times 0, okay? That's the formula here, 2. So that number 2 goes at the intersection. So it's gonna be first row and first column, so first row, first column here. That's this dot product result. And then you will go for the second one, you go first first row and second column here. So you go 3 times 4 plus 1 times 2 plus 0 times 1, and result goes here. So you just put the result at the intersection. So first row, second column, first row, second column. And at the end, you will get a matrix that's size of these outside dimensions. So 2 times 2, because this middle dimension will cancel out. And this middle dimension must be same, equal. And this outside dimension, outside doesn't have to be same. So if this was 2 times 3, this matrix and this matrix was 3 rows and 4 columns, then it's possible to multiply because 3 and 3 inner dimensions are equal, and the resulting would be 2 times 4 if this was 4. In Python, you would define matrix as an array of arrays. So this is the first row, this is the second row. Here it's being indexed as 1, 1. So here indices are starting from 1, maybe to show like example for you to understand it easily, but usually indices start from 0, 0. First row, second row. Just like here. So this is the first row, this is the second row. And this has 2 columns as well. So 2 rows, 2 columns. And so that's how we can define matrix in Python with, for example, NumPy. We can also do it with PyTorch and stuff. And this is example of 3 by 2 matrix. So 3 rows, 1, 2, 3, and 2 columns. Now these rows and columns are gonna take some time for you to understand intuitively quickly what's happening. Like 2 by 3 matrix, 2 rows and 3 columns. So we can print shape of the matrix. So a matrix, it's this one. So shape here is 2 by 2. And then we can print shape of the first row and shape of the first column. So let's see. Shape is 2 by 2, rows 2 and columns 2. It's maybe easier to understand on this example because here rows and columns are different shapes. So shape is 2 by 3, rows 2, columns 3. So if you say print a dot shape 0, that's gonna be the first number in your shape. So it's gonna be this number 2. And shape 1 of 1 with index 1 will be the second number 3. Maybe you want to play with this a little bit to see what happens. So This is going to show the number of columns. This is going to show number of rows. And so if you have a matrix 1, 2, 3, 4, 5, 6, you can access individual elements by just calling the index. So this index of this would be 0, 0. So if you say A of 0, 0, that will give you this value, which is, in this case, the value is 1. If I put it like this, it's going to be 10. So this value has index 0, 0. And that's how you can access the elements. I'm actually going to talk more about this indexing and slicing later. It's more for maybe PyTorch tutorial. So let's go on to matrix addition. I already explained this. So here you would just add each element with corresponding on the same index. So 1 plus 5 is going to be 6. The resulting will be 6. And then 2 plus 6 result will be 8. So same index. Scalar multiplication, you just multiply. So if you say 2 times matrix A, you will just multiply each of these elements with 2. So this will become 2, 4, 6, 8. So let's see the result here. 2 times A, you will just multiply with 2, or 0.5 times A, you will just multiply each element with 0.5. 0.5, 1.52. Minus 1, same, just each element with minus 1. Matrix vector multiplication is just like matrix multiplication. So you first need to make sure that the inner dimension is same. So 2 times 3, so this 3 must be same as this 3, 3 times 1. In this case, you can multiply A matrix multiplied vector V, but you cannot multiply vector V matrix multiply vector A, because then this inner dimension would not be same. So you can first put this first and then this second, and then that's how you can matrix multiply it. And then the result will be 2 times 1, because the inner same dimension will cancel out. And the step-by-step calculation goes like this. 1 times 2 plus 2 times 3 plus 3 times 4. And then that's going to be 20. And then 4 times 2 plus 5 times 3 plus 6 times 4, that's going to be 47. So that's the resulting vector. So you multiply this row with this row. Now this could be a bit confusing because I was showing you that you multiply row and a column. But depending on how you do it, how you code it, how you imagine it, this can also be done this way, because this is just a vector. So in matrix multiplication, the way we imagine it conceptually is row times column. But since this is just a vector, we can also imagine this as a column vector, being 2, 3, 4, and then this row and this column vector. So this is a bit confusing. You're gonna have to do this by yourself, by hand. Try to multiply, try to figure out, try to get intuition. Try multiplying this, try multiplying others, maybe get some other examples from AI, from ChatGPT. So the matrix multiplication example here, I explained it. So you can use this at as matmul, or you can use np dot, which is a bit confusing because this implies dot product, but this is actually, this is matmul. And so here you have step by step on how to multiply two matrices, but this is just something you would need to understand. And I saw Sam Altman explaining something about matrices, and he was showing this with his arms or hands. So that's how I know that he also knows how to multiply matrices. I was wondering if it was in his job description as CEO of OpenAI to be able to multiply matrices. I was always wondering that. This is transposing matrix. So we have 1, 2, 3, 4, 5, 6. We transpose that, it becomes, so we swap rows and columns. So it's now, this column now became the row. So 1, 4 now became the row. 2, 5 now became the row. And the shape is swapped now. Then we have identity matrix, where it's 1 on the diagonal and others are 0, and it's a square matrix. It has equal number of rows and columns. And when you multiply any matrix with identity matrix, it will remain the same matrix. So the result will be the same as this matrix that you multiplied with the identity matrix. And in Python, you can create identity matrix by saying np.i and then how many rows and columns. So 2 or 3 or whatever the number is. So this is the 2, this is 3 by 3, it can be any number. So identity matrix acts like the number 1 in multiplication, so it doesn't change the thing it's multiplying. Here are some properties. You can analyze them if you want. I just want you to understand that in matrix multiplication, you cannot swap the order of matrices. This is not generalizable. It's not true in general. There might be specific cases when it's true, but in general, it's not true. That's gonna be it on matrices. If you understand this, you understand everything you need to know about matrices as your fundamentals. So let's check out the last lesson as well. Lastly, let's learn about probability. This is extremely important. It's used in large language models, reinforcement learning, computer vision, natural language processing, everywhere. So you have a coin. Let's assume it's a fair coin. You flip it, you have 50% chance to get heads, 50% chance to get tails. Or you roll a dice, 6 sides, so you have 1/6 chance for any particular side to appear, to be rolled. Probability measures how likely an event is to occur. 0 means impossible, 0% chance probability. 1 means certain, 100% chance of probability always happens. And 0.5 means 50-50. So let's calculate probability of flipping a coin and getting heads. So we have 2 possible outcomes, heads and tails. But we are calculating probability for just one of those outcome, heads. So we say heads outcomes can be just one of those 2 divided by the total outcomes, which is 2, which is gonna give us 1/2 or 0.5 or 50%. So for rolling a dice, it's same. We just have 1/6 now because 1 side out of 6 possible. But in this case, we are assuming that each of these 6 sides has equal probability to happen. So then you can divide 1/6 to get your probability. Same goes for heads. If each of the heads or tails has equal probability, then you can divide. Here, if we flip the coin 10 times, we get 7 times head, 3 times tails. So theoretical probability is 0.5, but actual probability, measured I should say, is 0.7 or 70%. But as we flip more coins, the measured probability will get closer and closer to theoretical. So for 100 coins, we get 0.39, and for 10,000 coins, we get 0.5024. So this one, experimental, is very close to the theoretical. So the more flips or more samples, the experiment probability, measure probability will get closer to the theoretical. And so if we try that with dices, we will get with 1,000 rolls, we will get close to the theoretical of 0.1667. And here the orange one shows theoretical probability of each dice face, and it's always the same. But the measured one, it's gonna be a bit different. But if we do a lot more measurings, then this measured one will get closer and closer to the theoretical. Now, what is the chance that if we roll 2 dices, one dice gives us 1, and the second dice gives us 6. So it doesn't matter which dice gives which number. We just need to get 1 and 6. And the probability there would be by multiplying those 2 probabilities. So it's gonna be a lot smaller probability to get both of them. Now, what is the chance that in those 2 dices we get 1 or 6, but not both of them, just either 1 or 6. So it can be 1 on the first dice, or 1 on the second dice, or 6 on the first dice, or 6 on the second dice. So there are 4 possible ways to satisfy this. But If we get 1 and 6, that's not what we want. So we will subtract the probability of getting 1 and 6 because that's not what we're looking for. And so the probability of getting 1 is this, and probability of getting 6 is the same. And then subtract if we get both 1 and 6, and this is the probability that we get 1 or 6 if we roll 2 dices. Here we have probability distribution. So this is the task. If we roll 2 dices, what is the probability that the sum of the numbers of each dices, like we get 1 and 6, so the sum is 7. So what is the probability of each of these sums? For example, if the sum is 2, it means we got 1 and 1. If the sum is 7, it means we got 3 and 4, and 4 and 3, and 2, 5, 5, 2, 1, 6, 6, 1. So you can see that we can get 7 in a lot more different ways than, for example, 2, because we can get 2 as the sum if only if both of the dices are 1. But 7 we can get in a lot more different ways. So probability of the sum being 7 is a lot higher. And that's the probability distribution over all of these sums. So what is the expected value of a dice roll? We know that dice can show us numbers 1, 2, 3, 4, 5, 6. And each of these numbers has 1/6 chance to happen. So what is the average or expected number we will get by just rolling a bunch of times? You can maybe intuitively understand that the average number will be 3.5 because this is exactly in the middle of 1 and 6. But we can calculate expected value by multiplying the value we will get. So 1, 2, 3, 4 times its probability. 1/6 is the probability for each of these values. And then sum up. So sum up and divide by the number to find the average or mean. But this is very important. This summing up of all of the values and dividing by the number is just because every value has this equal probability to happen. That's why we can pull them into a bracket and then divide by this common denominator is the same for every one. But if these probabilities were different, not all are like same 1/6, then we would not be able to like sum up the values and divide by 6. So summing up and dividing only works if the probabilities are same. So that's like a shortcut you can do. But this is more general formula. You just do each value times its probability. And but this is more specific. This works if probabilities are same. Then we have conditional probability. So probability of A happening given that B happened. You can calculate this by this formula. So probability of A and B divided by probability of B. It's easier to understand this in an example. So given that we roll an even number, what's the probability that that number is 6? So first of all, probability to roll an even number is 0.5 because we have 3 odd, 3 even numbers on a dice. And probability of rolling 6 and even. So you need to think a little bit. So if you roll 6, it will also be even. So here we're just gonna use the probability of rolling 6 because if we roll 6, it will also be even. So that's the probability. And so the formula, we intuitively know that, let's first look at intuition. So we have 3 of these. So if we roll an even number, then because each of these even numbers has same probability, then it's 1/3, 1/3, and 1/3 to be each of these numbers because they have same probability. So that's what we will get in the result, 1/3 or 0.3333. So, and if we check the formula, it will actually come out as 1/3. So the probability of getting 6 given that we got even number is 1/3. And this is the law of large numbers. So if you have probability, theoretical probability at 0.5, you're flipping the coin. In the beginning, where you just flip maybe 10 times, maybe you will actually get 7 heads and 3 tails. But as you flip more, the measured probability will converge towards the theoretical probability. So that's the law of large numbers. If you have large numbers, they will converge towards theoretical probability. Now this is also interesting. Let's say you are tossing a coin 10 times. What's the probability that out of those 10 times you get 5 heads? I actually recommend you go to my channel and here in playlists you check out this Become AI Researcher probability, because this is a playlist of going into probability in a lot more details, and you can check just first video or first and second. Those contain most important things. So random variable, standard deviation, variance, and then continuous random variable, probability density function. So maybe these two first videos you can check. That's gonna be it on this part on maths. You can join my school to become AI researcher, link below the video, or you can find it on my channel, here on my channel. Get a 7-day free trial if you join right now. In this lesson, we will learn about PyTorch necessary for AI research. After this short course, you will be able to understand and code any neural network, any AI research in PyTorch. So I presume basic understanding of Python, you can learn that on YouTube if you never used Python. So here I'm gonna go into extensions. I am on VS Code or Cursor, and I'm just gonna say Colab, and I'm gonna install this Google Colab if I want to run my code on Google Colab from this local environment. You can also open these notebooks on Google Colab, or you can just run them locally. But here I'm gonna run on Google Colab from my local environment, but you can have whatever setup you want. So I will select another kernel here. So I can click here Colab, or select another kernel and Colab. And then I can start a new Colab server. I'm gonna choose CPU and just press enter for so here I'm just gonna use Google's CPU. And then I'm gonna choose this Python kernel. And let's see, it should work. And it works. I chose CPU because I can use it for longer than GPU. And if you don't have PyTorch installed, like you run this and it says no module named Torch, then you would just install, so you would pip install Torch in your console, in your CMD, right here. Pip install Torch, or in the Google Colab or wherever. So let's learn about tensors. So you can create a tensor. Tensor is like an array. It can also be array of arrays, or it can be array of arrays of arrays. So a number of nested arrays within arrays. So here we have a 2D tensor. I'm gonna zoom in. So it's like a matrix. So this is the first row, this is the second row, and the data type is float 32 here. So this is from Python. You can self-study what this is. This is from Python, so this is kind of a prerequisite, but if you don't know, you can ask ChatGPT all of these things that I skip. So if I go ahead and print all of this, this is the tensor that we have. This is its shape, so we have 2 rows, and each row has 3 columns, or so 1, 2, 3, 1, 2, 3. So there is 3 columns in total. So 2 rows, 3 columns. We can flatten this tensor, which means we will just convert it into a single array. And so it's gonna go like this: 1, 2, 3, 4, 5, 6. So we will just put rows next to each other, and it's gonna be a single array. It will not be 2 arrays like here. So the shape is now just 6 because there is 6 numbers in this one array. And this flattening is done with tensor.flatten, and t is our tensor, remember. So t is our tensor. And then we can also specify this start dimension to be 0. In this case, this will look the same as without specifying this start dimension 0. For me to explain what this start dimension does, let's look at a different tensor. It's a 3D tensor, so it's 2, 2, 2. So inner arrays have 2 elements. There is 2 of these, and then there is 2 of these outside. So it's 2, 2, 2. So if I say flatten, but start dimension is equal to 1. So we will actually preserve the dimension 0. We will preserve dimension 0, and we will start flattening from dimension 1. So what that means is we will not have one big single array. Instead, we will preserve these outside, these most like outer 2 elements, and then we will flatten within them. So we will flatten within these outer elements. So it will be 1, 2, 3, 4. Because we are preserving dimension 0 and we are starting from dimension 1. So you can play around with this and try to change it and understand what's happening here. Try to make bigger tensors, try to put some other dimensions. Now let's see reshaping. So we have a tensor 1, 2, 3, 4, 5, 6, 7, 8. And the shape here is going to be 2 rows and 4 columns. So 2, 4. And so we want to reshape for it to be 4, 2 instead. So let's see what it's going to do. It's going to group like this. 1, 2, 3, 4, 5, 6. So now we're going to have 4 rows and 2 columns. And it's going to just start from the beginning. So it's going to group these 2, these 2, these 2, these 2. Also, if we have a tensor 2 by 3 by 4, now I want you to understand what here is 2, what here is 3, with what here is 4. So you need to think about it. So this is 4, and then there is 3 of them, and then there is 1, 2 of these big ones. So you need to understand this. And we want to reshape this tensor to 6, 4. What is that going to do? That's going to create 6 rows, each row having 4 columns or 4 elements, so 4 columns. So in that case, this 4 will be preserved, and these 2 and 3 will be merged into 6. And you see that you have to have equal number of elements at the end. So 2 times 3 times 4 must be equal to 6 times 4. So you can play with this and try to understand what's happening and how it works if you change it a little bit. Now there is also view, which is similar to reshape, but I'll show the difference. So if we have a tensor like this, we say we want to reshape that to have 4 rows and 2 columns instead. So this will group 1, 2, and then 3, 4, and then 5, 6, and 7, 8. Like this. So this is interesting. So we created a new tensor that's gonna be t-view. So we have original tensor t, and t-view is the new tensor. But if we change t-view, it will also change original tensor, because t-view is actually using the same elements, the same memory slots in memory as this original tensor. So when we change t-view, we will also change this original one. So keep that in mind. That can be useful for some situations. So we see that the first element is 1 of both of them. And then we're gonna just modify t-view at 99. And then the original first element now also becomes 99. So now all of them are 99. So view requires tensor to be contiguous in memory, means all of the elements need to be next to each other in memory. Reshape will work even if the tensor is not contiguous, whether or not it's contiguous. So whether or not all of the elements are next to each other in memory or not. And it will create a copy of the tensor if necessary. if it's not next to each other. Join my school to become AI researcher. We have all of these courses that will lead you step by step. Get 7-day free trial if you join right now. Let's check squeezing. So we have a tensor that has elements 1, 2, 3, but there is another dimension around it and another dimension around it. So the shape of this tensor is gonna be 1, 1, 3, because the inner array has 3 elements, and then that array is an element of the outer array, and then that array is an element of the outer array. You see here. And so we can use this command t.squeeze. So now we're gonna create a new tensor. T-squeeze is equal to t.squeeze. And this will remove all of these outer dimensions that have just dimension 1. So now we will just be left with this tensor, or this array I should say, or whatever, it can be also tensor. But the outer dimensions that have one element will be removed. That's what squeezing does. We can also specify at which dimension we want to squeeze. So if we look at this tensor, and can you tell me what the shape of this tensor is? Because there is 3, but 3 is an element within an array. And then there is 3 of those elements, or I should say 3 of those arrays. And then there is this outside. So the shape of this is 1, 3, 1, because there is 3 of these and each of them has 1 element inside, and there is like 1 outside dimension. So if I say I want to squeeze at dimension 0, this will remove this outermost dimension. So let's see what happens. Now this has removed this outermost dimension, and so we just have one array of 3 of these arrays, small arrays, 1 element arrays. So you can play with this and understand how this works. I can also squeeze at dimension 2, so t2.squeeze. And remember, t2 is our original array. So this is not our squeezed. I'm not squeezing already squeezed array. I'm squeezing now the original array again, or I should say tensor. So squeeze the dimension 2 here. So this will remove, you see here, so every element was originally in its own array, but I'm going to remove that dimension 2 here. So now these elements will no longer be in its own array, and so we will just have these elements in this. So now it's 1, 3. So because we removed this, and now it's just 1, 3. And unsqueeze does the opposite. It will add the dimension of size 1. So if we have some tensor 1, 2, 3, 4, we say unsqueeze at dimension 0. So the previous shape was 4, and then we unsqueeze at dimension 0, so it will add 1 dimension at position 0, and it will have size 1. So now that means we have another array outside of this original tensor. And we can also unsqueeze at dimension 1. So if we take this unsqueeze at dimension 1, it will be 4, 1 now, because it will add dimension after this. And that means that each of these will be in its own brackets, or I should say in its own array of size 1. So this is the difference between unsqueeze at 0, unsqueeze at 1. You can play with this and understand like how it works and why it works and what it does. You can also unsqueeze at -1, which will add dimension at the end. So so if you don't know the actual shape of your tensor, but you just wanna put every element in its own array, then you can say unsqueeze at dimension -1, and this will put every element in its own array. So it will add another. So even if every element was already in its own array, it will add one more. array within that array. So every element will just get brackets around it if you unsqueeze at dimension -1. This is good if you want to separate. If you have some array and you need to separate it for something, do some operations on every single element. So that's how it works. So we are now at the first lesson here, first notebook. I'm gonna show you how to create different types of tensors. So we can do torch.zeros 5. That's gonna just create a tensor of 5 zeros, but whatever shape you put here, like 3, 4, it will create a tensor with this shape with all zeros. So 3 rows, each row has 4 elements or 4 columns. So 3 rows, each row has 4 elements. We have ones and this full, which we can specify the value. So ones 5, this will create an array of 5 ones, or this matrix of ones. Let's see what it looks like. So array of 5 ones, or matrix with this shape, or a matrix where each value is 5. You can also convert numpy array to a tensor. So if you have numpy array, you just say torch.from numpy to convert it into a tensor. And you can take the tensor and say .numpy to convert it back to numpy array. So if you check the classes, it's either gonna be torch tensor if it's torch tensor, or numpy.ndArray. And when you convert them, so when you use torch.from numpy, it shares the memory with the numpy array. So when you change this new torch tensor, it will also change the original numpy array variable. You can also, if you clone, so that will create a separate copy. So then it will be separated, the numpy array and the tensor. You can also create tensors with random values. This is used in neural networks when initializing weights. So you just say torch.rand and then the shape. And you can also specify, you can also use rand int to make it integer between 0 and 10, but 0 is included, 10 is not included. So 0 is inclusive, 10 is not inclusive. Or maybe exclusive. This is our first. So this is example of the first thing we did here is torch.rand 3, 4. So that's gonna give us these numbers between 0 and 1. And so 3 arrays or 3 rows, and each row has 4 columns. And then the second rand int will give us integers like this between 0 and 9. We can also create random values from normal distribution where mean is 0 and standard deviation is 1. So if we use torch.randn, so this should be bunched up around 0. These numbers should be very close to 0. And then the further away you go from 0 in positive or negative, there is less probability, although you can get any number here. But the further away from 0 you go, the probability decays exponentially. So you're usually not going to get numbers that are too far away. But you see, we get even numbers larger than 1. So we also have, you can also use this trick because torch.rand will give you values between 0 and 1, but you can multiply all of those values with 10, so then they will be between 0 and 10, or yeah, 0 and 10. So here we can see that values are between 0 and 10. You can also print data type of the tensor, so it's gonna be float if you initialize it like this, but you can also specify data type to be int64 or float32, because originally it's float32. You can also convert. So if you have int64, you say dot, so that tensor dot float, it will convert to float32. For the next one, you would need to know how matrix multiplication works in mathematics. So you can just watch my video here, Math for AI Research, or you can just type here like how to multiply matrices, matrix multiplication on YouTube. So if you know how matrices are multiplied, dot product between this row and this column, so you need to understand that. Then we can go further, go on, and this is the operator to multiply matrices. So you can also use torch.mathmul, by the way. So if you have this matrix and this matrix, the result will be this matrix. Of course, the same result, depending on which you use, @sign or torch.mathmul, the result will be the same. One thing you need to know, so when you have matrix and vector, you multiply them the same way. You're gonna get some other vector. Now, you can imagine this vector as being some vector, and this resulting vector as being some other vector. So the rule in maths is when you multiply vector with a matrix, that matrix will rotate and squish or stretch the vector. So that's what matrices does, and this is important in neural networks if you want to do this theoretical or research and stuff. So just know that when you have a vector, you multiply it with a matrix, it's gonna stretch or squish and rotate the vector. Possibly rotate. It may not rotate, by the way. I will go to third lesson, third notebook here in PyTorch. So I'm gonna skip some of the matrix stuff. That's not so important. If we have a tensor, in this case it's a matrix, we can transpose it by using a.t, and I'll show you what transposing means. And we can use a.t with these brackets, but only for 2D tensors. So this is what it's gonna do. It's gonna swap rows and columns. So this was a column, now it's gonna become row. 1, 4 was a column, it's gonna become a row now. 2, 5 was a column, it's gonna become a row. And you see that 1, 2, 3 was a row, now 1, 2, 3 is a column. So it's swapping rows and columns, transposing. Let's see if we have a 3D matrix. 1, 2, 3, 4, and then that's one matrix, and then there are two matrices, and we want to transpose the zeroth, so that's going to be this outer dimension and the last dimension, which has index 2. So that's going to be a little bit weird. So now we did this, we say 1 and 5 now becomes this row. So now the first elements of the outermost dimensions, which are these two, now become elements of the innermost dimension because we transpose them, we swap them. And then the innermost dimension elements in the previous become outermost dimension first elements. So 1 and 2. So this is going to require some intuition, some playing around, some understanding like how this transposing works. We can also rearrange dimensions. So now we are, in this case, we are reversing the order, but you can put any order you want. So let's see what happens when we reverse the order of dimensions. So the original one is 1, 2, 3, 4, 5, 6, 7, 8. But then 1, 5, 3, 7. Let's see. 1, 5, 3, 7. It's a little weird. 2, 6, 4, 8. So this is something that you just need to kind of look at this and get the intuition why these numbers, how, what's swapped, etc. So indexing and slicing. If we have a tensor 1, 2, 3, 4, 5, 6, 7, 8, 9, then we can index. So this is this element has indices 0, 0 because it's 0 row and 0 column. It starts from 0, not from 1. So then this element would have 1, 1 because it's, so this is 0th row, first row, second row, 0 column, 1 column, 2 column. So this has 1, 1. This has 2. So this has, no, this is 1, 2 because row 1 and column 2. So we see that T of 0, 1 is 2. So 0th column, 0th row, first column. That's going to be 0th row. And then column 1, that's going to be 2. You can also access entire row. So this will give you entire row. And let's see, 1, 2, 3, entire row. And you can also get the first column or entire column, not the entire column. But you need to put this sign here. And this means get all of the rows in the 0th column. All of the rows in the 0th column. So all of the rows, but only in the 0th column. So 147. So 147 is it's gonna be our new tensor. And you say all of the rows in the column with index 1. So there's gonna be all of the rows, but in this column with index 1, 258. 258. Now let's see slicing. So if you say t and then you say 0 to 2, this will give you all of the rows starting from the 0, including row 0, until 2, but excluding 2. So this is excluded. This is inclusive, this is exclusive. So starting from here until here, but excluding this one. So it will just give you these two. 1, 2, 3, 4, 5, 6, 7, 8. Let's see. 1, 2, 3, 4, 5, 6, 7, 8. And then I'm gonna now go a bit quicker. So this will go from row 1 to the end. So from row 1 including until the end. So it will give you these two. You can check below. So this will give you from the beginning until 2, but excluding 2. So from the beginning, so it will give this one and this one, and it will not give you 2. This is index 2. So this is index 0, 1, 2. It will not give you 2. From the beginning until 2, but not 2. Okay, and then you can also say columns. So because you have comma here, this is where you select rows, and here this is all rows. This means all rows. So from the beginning to the end. And in this case, end is also included. So when you have this, it's from the beginning to the end in rows, and everything is included. So from 0 to 2 columns, but 2 is not included. Okay, so we got all of the rows, and then 0, 1, but 2 is not included. So it should just give you these two. 1, 2, 5, 6, 9, 10. Let's see. 1, 2, 5, 6, 9, 10. Okay. We can also get all of the rows and from 2 until the end. So that's gonna say, let me see here, 3, 4, 7, yeah, that's it. So from 2 including 2 to end columns. And you can also pick like this. So from 0 to 2 excluding 2 rows, and from 1 to 3 columns. So from 0 to 2, and from 1 is going to be this one, 2, 3, but excluding 3. So this will just give you these middle, what was the columns? So it will give you this middle matrix. You can also create a Boolean mask. So let me show you what that is. So if you have a tensor 1, 2, 3, 4, etc., you can say mask is equal to tensor t greater than 5. So what that's gonna do is replace everything that's greater than 5 with true. All of the where the value is greater than 5. So this is 1, 2, 3, 4, 5, okay? And then this is greater than 5, 6, 7, 8. These elements will be replaced with true because these are the values. So if I was to put number 7 here instead of the number 1 that was originally, then this would also be true because this element would also be greater than 5. So all of the elements, values that are greater than 5, they get replaced with true. And then you can use that mask that you just created. So you can say t, original tensor t of mask. It will give you all of the elements that have the true assigned to them, like so 6, 7, 8, 9. You also can do this conditional indexing. So t where the value is greater than 5, or t where the number is even. So value divided by 2 gives remainder 0. So these will give us greater than 5 and even numbers. You can also modify values like this. So t, where the value is greater than 50, you want to replace all with 0. So everywhere in this tensor t where the value is greater than 50, it will all be replaced with 0. So let's say we have these values here, 100, 200, 300, 400, and then it's gonna get replaced with 0, because if we put it this way. Now let's learn about concatenating tensors. So if you have two tensors, 1, 2, 3, 4, and 5, 6, 7, 8, you can just concatenate them in dimension 0, or concatenate them or join them in dimension 1. Let's see what both of those do. So concatenating at dimension 0 will just append all of these rows. Now it's all gonna become like a bunch of these rows. You see, 1, 2, so this guy, then just continue with this row and this row. So now they're concatenated like that. So it's 4, 2. The new shape is 4, 2. This dimension got concatenated. The first dimension, dimension 0. And if we concatenate on dimension 1 or second dimension, then it will go like this. 1, 2, 5, 6. So the first element here and the first element here will get here. And then 3, 4, 7, 8. And now the shape is 2, 4. So this also requires some playing around, testing. You need to see like what happens, try to understand it yourself. This is something that's that you just need to play around with and understand. You can also concatenate 3 tensors, and it's done with torch.cat, I forgot to say. So 3 tensors, it's gonna do the same thing. So you're just gonna say 1, 2, 3, 4, 5, 6, etc. So the same thing. Now it's 6, 2. You can also torch.stack. If you have 2 matrices, 2 by 2 and 2 by 2, you can kinda just put them into another array, another tensor. So this first matrix will be the first element, and the second matrix will be the second element of this. So now the shape is 2, 2, 2, because you join these two matrices into like another array now. So that's what you can do with this torch.stack tensor 1, tensor 2 along dimension 0. Now I'm in the last 7th lesson. Let's see some more tricks. So we have identity matrix. If you say torch.i3, let's see, this will give you this identity matrix where it's ones on the diagonal and zeros outside. If you check my math course, you will see that multiplying any matrix with this identity matrix will give you that same matrix. This is like multiplying with 1, this identity matrix. So if you have any matrix, you multiply that with identity matrix. So matrix multiply, it will give you the same matrix. Torch.arrange 10 will give you an array from 0 to 9, because this is excluded. So integers from 0 to 9. Let's check here, 0 to 9. Torch.arrange 2 to 8 will give you integers 2 to 7, because this last is excluded. 2 to 7. You can also say arrange 0 to 10 with step 2. This means it will go 0, 2, 4, 6, 8, and 10. The last one is excluded. You can say step 0.5. So it will go 0, 0.5, 1, 1.5, until 4.5. You can also set data type to be float 32. Then it will give you this like 0 dot, 1 dot. So these are the floats. And this is what you will often do, is you will arrange and then reshape. So this will give you numbers 0 to 11. So there will be 12 numbers. And then reshape to 3, 4, 3 rows, 4 columns. And this is what it's going to look like. You're going to do this often. Linspace will give you the following. So if you say 0 to 1 and 5 values, so it will give you 5 values in between these numbers, equally spaced, including these two numbers. So starting from 0 to 1 and in between, and it's evenly spaced, 0.25, 0.25. So then you can also say from 0 to 10 and then 10 evenly spaced numbers. And you see here in linspace, this 10 is also included. So previously it was excluded, but now it's included. You need to just memorize that that's how it works. From minus 5 to 5, 11 numbers. So in this case, it will just be the integers. And this is interesting. If you say torch.empty and then the shape, so this will create a tensor or in memory, but it will not change the values. It will not set any values. So it will just allocate space in memory. So whatever numbers or values were in the memory, it will have these values. You see, we have some garbage values here because we did not change them. We just took the memory, but we didn't change anything. So that's gonna be it for this video. Check out the GitHub, check out the previous course on math, join my school, and see you in the next video. Let's learn about neural networks. After this lesson, you will be able to code your own neural network from scratch. You will understand how this works, and you will be able to then further build it into projects and AI research, etc. Make sure to have PyTorch installed, NumPy, Matplotlib as well. You can find this repository at the GitHub below this video. So this is a neural network, but let's just first focus on a single neuron. So let's just look at this first blue circle and the first white circle and this output. And let's imagine none of these other exist. So input would be some number. And then it's multiplied with some weight. This weight is learned by the neural network. So this weight will also be some number. And when input is multiplied with this weight, it will give some output. So the output is gonna so the neural network will transform this input into output, will predict something. And the weight that's multiplying the input and transforming it into output is gonna be learned during training. So what is the best weight that's gonna give us correct output based on any input? That's how neural network learns and then generates or predicts. So let's check code example. Let's say we have inputs 2 and 3. And then these would be weights. These would be neural network weights like 0.5 and 0.3 that are learned, that are already learned. So we'll see later how they are learned. Now we could also have a bias. It's just a single number that's added for the entire layer, entire set of weights. Entire set of weights has a single bias number, and you see here the output, the weighted sum, it's gonna be this weight times this input plus this weight times this input, and then at the end we have some bias. So bias is also learned. It also helps, if you know functions, bias will help this function, whatever it is, to move left and right. And these weights are gonna determine the slope. So this is in my math course for machine learning that I published earlier. In this case, this is just a dot product. Right here is just a dot product between input and weights. And so weighted sum is 2 in this case. And then because this is gonna be some linear function, if we wanna make it maybe curved, we need to actually pass this through some activation function, for example sigmoid. Now when we pass this output, weighted sum, through some function like sigmoid, it looks kind of weird, but let's just ignore like whites like this. Let's just imagine that sigmoid is gonna make this function like curved. So if you have some data points here, you wanna actually separate them with a curved function. If you have a straight line, then it will not separate these like messy data points. So you need to be able to curve the function to separate the data points. That's what activation function will do. It will take this weighted sum, which is a line, and make it curved. And so at the end, for these specific numbers, we get this activation or output. So this here is sigmoid function. We also have other activation functions like ReLU, and their purpose in neural networks is to curve the lines that are, because lines we get with just multiplying weights and that bias are straight lines. Because here, let's say we want to separate maybe this red data set. We cannot do it with a straight line because it can just like cross over it. We need a curved line that goes around this like this. So that's why we have activation functions to curve the lines. So that's how neural network will be able to learn how to separate these datasets. But let's see on some examples more. Join my school community to become AI researcher, link below, or you can find link on my channel here in the about section. So usually you would first initialize a neuron. So weights would be initialized as random numbers from a normal distribution. I explained that in previous PyTorch lesson on my channel. And then make it very small. So maybe these would be around like 0 to 1, a bit more maybe. But we will make them all very small, so they're around 0.1. Bias goes at 0 because bias is being added, so in the beginning we add 0. But you don't want to initialize weights at 0 because weights are multiplying. So whatever, then they will just turn everything to 0, so that's not good. You want to initialize weight with some number. And here we would instantiate this class, neuron, and let's say number of inputs is equal to 2. So then this will create 2 weights and 1 bias. So this number of inputs just influence the amount of weights. So this is example. Number of inputs 2, and these are the random weights that we generated. They're really very small because we multiply with 0.1. So then to our neuron class, we want to add this weighted sum function. So it will take inputs, the numbers. So this is different from number of inputs. This is the inputs, the actual inputs numbers. And this will do dot product between weights and inputs. Now this is also matrix multiplication. It says here dot, it's a bit confusingly named, but this is matrix multiplication between weights and inputs, and then add bias at the end. And then we're also going to add this part to our code. So after we initialize, we already seen this part of initialization. We want to add this part. So I set some inputs here, and then I call neuron.weightedSum. I call our new function to do matrix multiplication. So the weighted sum here is 2, which also includes this bias, by the way. Now we will add a third function to our neuron class, which is going to be this sigmoid function. And so it makes it non-linear, so it curves our line, because when we just multiply with inputs with weights and that bias, it's going to be a straight line. The function is going to be a straight line, the function of weights times inputs plus bias. But sigmoid makes it curved, or activation function makes it curved, and we will use sigmoid because it has like a nice curvy shape that neural network can use well. So this is the formula for the sigmoid function. We need to pass in this number, and then the formula is 1 over 1 plus e2 minus x. And then we will just pass our activation, or I should say the output of the weighted sum, through sigmoid, and we will get some activation value. Sigmoid will be between 0 and 1 like this. It's gonna be curved, so if neural network needs to make this maybe left curve, it will make weights and biases such that we get some number around -2 and -1 or something like that. And then after activation, it will get this left curve to maybe encircle some data. If it needs this other right curve, then it will learn its weights and biases to give a number around 1, 2. So it will get this curve here to encircle some other data in this way. So this activation function will never change. It's just the weights and biases. But then neural network will learn to adjust weights and biases, so when the output is passed through activation function, they will properly encircle data or be able to predict or generate data. That is, it will have proper understanding of the data. Now we can test this with different inputs, So 0, 0, 1, 0, 2, 3, and you will see that the output is always some number between 0 and 1. We can also try different activation functions. So sigmoid will give 0.8, relu will give 2, this tanh will give 0.96. So depending on the activation function, you need to find one that works well for your dataset. For example, relu is very easy and fast to compute, but it's not as powerful. So maybe if you need some quick and easy task. Now let's see how to combine multiple of these neurons, not just one, into a neural network layer. So again, we will have input 2, 3, let's say, but then we will have two neurons. The first neuron is this one, 0.5, 0.3, and the second neuron is 0.2, 0.4. So you see that it has weights for each of the inputs. And we will have two biases, so one for each of the neurons. And the forward pass is the matrix multiplication between inputs and weights transposed. So I explain matrix multiplication in math and PyTorch fundamentals, but you can also check how it works, but you need to transpose weights here. Now, some people can also write like weights, matrix multiply inputs or inputs transpose. Now this just depends on how you save your weights in memory. You know that matrix multiplication, there are some rules. But for now, let's just take it as is. So inputs at weights transposed plus biases. So we have input tensor at weights transposed. At the end, we get this output, 2, 1.8. And then if we pass it through sigmoid activation, each of them will be some number between 0 and 1, depending on the input here. So here we would define a class layer, and then it would have number of inputs and number of neurons. So these are like hidden neurons. It can be different number. You see here we have 3 inputs, but 5 neurons. 5 hidden neurons, I should say. And then one output at the end. So in our linear layer that we initialize, we have number of inputs and number of neurons. And weights are gonna be number of neurons, comma number of inputs. This is one of those weird things that you just need to kind of get the intuition by trying and understanding. So number of neurons is 3, means we have 3 rows, 1, 2, 3 rows, and number of inputs is 2, and that's the second dimension here. So we have 2 columns. So in each row there is 2. So 2, 2, 2. So 3 rows, 2 columns. And that's why we also need to transpose, because we have 2 inputs. We need to transpose this matrix. So because of matrix multiplication, we will multiply these 2 and these 2, and then these 2, these 2, these 2, these 2. So we need to transpose, flip the matrix of weights. But I recommend you just try to understand this yourself, or you try like playing around, see what happens, try to draw. Understand how matrix multiplication works first. You need to practice this. These are the example weights that are initialized, and the input is 2. So when you multiply input matrix and weights matrix, you need to transpose this, because you are multiplying a row of the input with the column of the weights. So you want to multiply it with this row, but you cannot multiply row and row. So you need to transpose this row to become a column. So now it's just 2, 2, 2, like this. So then after initialization, we will add this weighted sum. And here we just do inputs, matrix multiply, weights transposed. We need to transpose them as I explained, plus biases. And at the end, you will get something like this. We will get 3 numbers, because the hidden number of neurons is 3. You know, we are multiplying 1 times 2 matrix of inputs times 2 times 3 matrix of weights. So the result will be 1 times 3. So this is matrix multiplication. So you have these 3 neurons that you get as a result. So again, I recommend you try this out yourself, change some numbers, try to understand how this matrix multiplication works. And then it's very easy to add this activation function. So torch.sigmoid and pass in the neurons. So before the activation, the numbers that we got of the neurons are these, and then after activation, it's gonna be this tensor or vector. So after we have this sigmoid, we would add that to this forward function. So in the forward function, we first do inputs times weights plus biases, and then pass the result through sigmoid activation, and then that's the output. Those are the neurons that we get. And so we can say output is equal to layer.forward and pass in inputs. This is how you would usually do it in neural networks, large language models, reinforcement learning, everywhere. Here we can take a look at some activation functions. So I already explained sigmoid. It puts any value on x between 0 and 1. Output is always between 0 and 1. We also have relu. This is very easy and quick to compute. So if the input is lower than 0 or 0, it will just become 0. The output will just become 0. And if the input is larger than 0, it will just remain that same number, whatever it is. So r of z is our number, is going to be maximum between 0 and z. So that's the relu function. You just find set 0 or z, whichever is bigger. This is very fast to compute. You would use this if you need some quick computation that's not so maybe powerful or precise, but you just need some easy task for the neural network, and maybe it can do it with this activation function. And you see here, it would just, if you have a line, it will maybe make that line like this. It's not going to be curved. It's going to be like this, just like cut or broken like this. But it will be a continuous line. It will not be like separated. But for some tasks, it's not good if you make outputs that are lower than 0, exactly 0 always, so you kind of erase all of that information. So there is a leaky relu. So outputs that are lower than 0, it will just make them a lot closer to 0, but not 0. So it will just squish them towards 0, but they will still not be 0. So they will be 0.1 times x if they are lower than 0, or they will just remain x if they are higher than 0. So this doesn't erase completely information like the relu function, while it still provides nonlinearity, this bending, so the neural network can use this bending to encircle some data. Here we have some examples. You see, this is the 0, so relu is just 0, and then gelu is actually more curved around 0 here, so it preserves information if the number is around -2. So, and then we have elu that's kind of going down even more. So we have these different activations. You would test which ones work best for your data. Here is another example: sigmoid, relu, silu, swish, elu. They're all kind of similar, but they do a bit different things. But they will all curve your line of weights and outputs and neurons. You see, with just multiplying weights and inputs and biases, you would get a straight line, but then passing that through activation function, you would get a curvy line. This is a good example as well. You want to fit this data with a straight line. It's going to be tough. You're going to have to leave out a bunch of this red data on the other side, which is wrong. But with a curvy line, maybe this is a sigmoid function here, you can fit data properly. Now, to understand how neural networks learn, I have 3 good videos. So you can watch this one, backpropagation from scratch, torch.backward, and this one where I train a neural network. I'm gonna leave all these links in the description, or you can just search for them. I also put these 3 videos here in the 3rd lesson after these neural network and layer and stuff, so you can just copy these URLs. That's gonna be it for this video, and see you in the next one. Welcome to attention mechanism and self-attention in transformers in large language models. So let's say we have a sentence: the cat sat on the mat. Let's say we have just these words in front of the mat, and we're trying to predict the next word that is mat. So how do we know what's the next word? Well, we're gonna take some information from the previous words. So we have 2 challenges here. How do we know from which words to take information? For example, here, cat set. That would give us most clue that this could be like a mat. So how to select previous words and how to actually take information. How do we actually like take information? What does that mean? How is that done? So in this example, we see that cat is selected to have 60% relevance, set 20%, the 10% on the, these are have smaller. Okay, and so you can ignore this last. Imagine this doesn't exist. So I'm explaining like how to generate this in this case. Attention weights will sum up to 100. So do they sum up? I think they do. Okay, but if we didn't have this 3%, this one, then this 3% would actually be like within these as well. So these would sum up to 100 if we didn't have this last word that we are trying to predict. So model learns to which word to focus on. The way LLM works is if you are predicting this word met, it's gonna take this word, previous word, the, and combine, add all of the relevant information into this word. So now this word will have not only this word, but all of the context before it as well. And then after processing, this is done like many times over and over again. It will just convert the final vector that's juiced up with all of the previous information into this next word. So how do we juice up this vector with all of the previous words, all of the previous information? So every of the tokens, including this one, will create three things: query, key, and value. This is confusing, but bear with me. So each of these words or tokens will be like a vector embedding. It's a vector. You can check my previous lessons, math, PyTorch, and neural networks to understand this. So it's a vector. And so that vector will transform into three vectors for each of the token vectors. So each of the tokens here, each of them will get three: query, key, value. And usually these query, key, and value are a lot smaller, 5-10 times smaller than this big token embedding. So this token, vector token embedding, represents the meaning of these words. So just these numbers represent meaning. So for example, large language model learns what each of the numbers in the vector, each of the dimensions represents. For example, maybe the first number in the vector represents if something is green. So the higher the number, the more this token has this green characteristics. So for example, if you have like some green apple, the first dimension will have a lot higher value than a word heart that's associated with red, for example. So the first number, first dimension in the vector of word heart will have a lot lower value. So a neural network will learn what these features are. And in this vector is same size for every token. It represents the token, it's same size. And the position, the dimension, first, second, it's always the same. So 0th dimension always represents the same thing for every token. Like how green is this? So each token will have query, key, and value. Query says which information am I looking for? And then key says which information I have. And the value is the information that it gives. Now, keep in mind, there is a difference between explaining which information you have and that information. So that's important difference. So if we are on this word the, its query will dot product with all of the keys individually. Okay? So if these words, these tokens query dot product, this token's key, as I said, the key is explaining what this token holds, what's information. If the dot product is a high number, we call that high affinity. Then you will just multiply the value of this token, the value, which is the actual information it gives, with that number, with that dot product of the query and key, and add to this, to value of this token. Okay, in the end, we are just adding values. But the query and key have two functions. How much to weight the value, how much, so do you want to reduce? So if you multiply the value of this with a small number, then when you add that small number to this value, it will not influence a lot, because this value will be multiplied with like 0.01. So when you add that, it's a very small number in each dimension, so it will not change too much this. And if that 0.01 is like the dot product between this query and this key, it means like I don't care about this information too much. There is no like affinity there. But if that product is high, it can be larger, close to 1, for example. Let's say 0.9. Then when you multiply this value with 0.9 and add, this value will have a lot stronger influence, because now it's a lot larger number than when you multiply it with like 0.01. So basically, to repeat, if you are predicting this token, then you look at this token and you add all of the values to the value of this token. Now remember, I said we're not adding the vector embedding of this token, of these tokens. We are adding we are transforming that vector embedding using a small neural network, one layer neural network, into a value vector. And value vector is a lot smaller than the big vector embedding. So we don't actually need to have so much processing. We don't need to work with the huge vectors. We can just transform it to small vectors for faster processing, and it's sufficient and enough to do this. So we just add values of each of them to this last known token. Add those vectors, add the vectors. But how much of the vectors we add will be decided by the query times key. So query of what I'm looking for, what I give. If that number is low, then it means like, okay, I don't really want what you give, or I just want a little bit of what you give. So then the value will be multiplied. The value vector will multiply with that small number, so you will just get like a little bit of influence here when you add that weighted value to this value. In the end, all of the values will be added to this value, and maybe this cat value will have a high multiplication number, high weight. And so it will give a lot of context, influence this value. And then set can also give a lot of context, so be a large number as well. So this is the self-attention formula. In this case, so this is where we start. So query, this is a query vector of this token, current token. Actually, in this formula, this is meant like for matrix of all of the queries of all of tokens. But not to complicate, let's just focus on a single token. So query of the current token times all of the keys of every previous token. So instead of calculating keys one by one, so query times key, query times key, query times key, we put all of this into matrix. And we calculate this vector with this key matrix. And transpose is just because that's how you do matrix multiplication. So that's why it's like here, it's like to indicate it's a matrix multiplication. You need to take care like which dimensions, what's transpose, what's not, which dimensions. But basically you multiply, so this is gonna be your query, this is gonna be your keys, for example, or you can have query like this and keys like this. It's just a matrix multiplication. And then this is dividing, because here, as I said, you just have one query. So the result will just be also one vector. And you want to kind of normalize that vector. If it has some large numbers, neural networks don't like large numbers. It's a bit tough to explain, but mere multiplication of large numbers, it behaves differently and it can influence. So not to overcomplicate it, we'll explain that later. Neural network learns better if the numbers are small, between 0 and 1, or maybe a bit bigger than 1, but not too much bigger. So that's why we just multiply by the square root of the number of dimensions of these key or query. So for example, if queries has 500 dimensions, it's a vector 500 numbers long, you divide by the square root of 500, and key and query will have same dimension. Then comes this softmax. So remember, this is result of this is just an array, and it has some numbers. So maybe biggest number would be here. It's just dot products. So they don't yet add up to 1 or to 100%. They are just like big number here, a bit smaller number here, smaller. So you need to make them add up to 1 or 100%. That's why you do softmax. You pass them through softmax, so they all add up to 1 or to 100%, while retaining their relative position. So this guy that had the biggest dot product will still be the highest. We'll still get the highest percentage. Let's see this on an example. So these could be our values. So this is a value vector for the cat set, and these are our weights. So it means like to generate the next word, this is 10% important, 30% important, and 60% important. And so we multiply 0.1 times this first, and second 30% times this, and this times this, and then we add up all of the vectors. We add them up, so we add first dimension here after the multiplication. So first dimension, second dimension, so we add element-wise vectors. We get just one vector, so 4 values. It's called like a weighted value vector. This is the example, so multiply each vector. So you get these numbers, and then you add this guy goes here, this guy goes here, this guy, so you add all of the third elements into this, all of the fourth elements into this. So this is the weighted value vector that you get in the end. And now this output will be kind of dominated by this third vector, because you see these values are very small because our weight is 0.1. And these values are gonna be biggest because our weight is 0.6. So the output will be dominated by this because it has large weight. Here I explained query key value again. So example, so query is what I'm looking for. If processing the word set, the query might encode, I need to find the subject of this action. So then it will fire when it sees a cat, it will fire. So when you have a query of the word set and it sees word cat, it will have high dot product between the query of the word set and key of the word cat, because this query learned to adjust its weights to look for nouns or subjects. The key, for example, of the word cat might say, I am a noun, an animal, a potential subject. So, as I said, it's gonna have this key vector, and key vector will just have a high dot product with this query vector. That's how neural network just learns those weights to get a high product between set and cat. And value is the actual vector that gets added up, the actual information it gives. So it's different from describing what it has. The key describes what value has or what value will give. So if you go down in my school, here we have learned to code and build LLMs from scratch. You can check a few of these. I'm actually explaining all of this over and over again in all of these. So it will just require like a lot of practice explanations. I'm gonna add more exercises videos. So that's gonna be it for this video, and see you in the next lesson. Welcome to Self-Attention lesson. Here we will focus more on code, so you can check the first lesson, attention mechanism explained. And here it's like code implementation. So key, query, and value, which I explained, are all linear layers. So I mean, they are created with linear layers. You pass in embedding dimension, which is the vector dimension, the model LLM dimension. And in this case, we will have the same dimension for the query and key and value, okay? Sometimes you can have smaller dimensions here. But, so this will just go from embedding dimension to embedding, but it will transform. So it will have some weights and transform this vector embedding into its query. So this query will say what information is this token looking for. I explained this in the last video. Key is describing the information and value is the actual information. So key is describing what value is. And all of them are linear layers that generate this key, query, and value, and same input. If we scroll down a bit, we can see a classic example in a large language model where you have sequence length, which are just like your conversation, your words. So your context window when you talk to ChatGPT, okay? And batch means there is like a multiple context windows, multiple independent conversations, okay? And every token in that sequence is represented with a vector. So that's why we have vector, or this is token, sequence length, and batch, which can be this 32 conversations. I changed it to conversations. Each conversation has 100 tokens and 512 dimensions, for example, for each token. So we pass X, all of this entire thing. We generate the queries for every token. Okay, so there is 32 times 100 tokens. Generate query for each, key for each, value for each. That's how we code it. And so we have query matrix, all queries, key, value. So the scores are calculated with queries at queries, matrix multiply key transpose, where we transpose the last and second to last, because that's just how matrix multiplication works. This is for the reasons of matrix multiplication. You need to have this transposed, and that's it. So the shape will be batch size, sequence length, sequence length. So here, every token will have score with every other token. So there will be score between every single pair of tokens. So it's like a square. That's why they say attention grows quadratically. For every token, you need to add all of the previous tokens to the score list. So the scores, again, you can imagine a similarity between these two tokens, or I should say affinity, or how much this token cares for this other token, how much of its information it wants to take, its context. And then we will just scale them back for stability reasons. So this means like square root. So this is the square root of the embedding dimension of the dimension of the queries or keys. And then we apply softmax to scores to put them between, like, add up to 100%. So we have like percentages. And then those are weights. So now for every token, I explained this in the previous lesson, but here we wanna, for every token, we take its value and add all of the values of other tokens, but weighted. So if for this token, like this other token is very important, then this attention weights will actually multiply its value with a high number, and then we add, just like add element-wise, this vector. But if some value is not so important, it will get weighted by a smaller, multiplied by a smaller number, smaller attention weight. And now this condensed or squished numbers that are around maybe 0 will all get added to this value. So it will not influence too much this value that it's added to. So it didn't take too much context from this token. I explained this in previous lesson, you can check also. So then you would be able to just define self-attention with the dimension you want for keys, queries, values. And then you would just pass in some x through the attention, and you should get the output immediately, which is a list of values for each token that's juiced up with the context from other tokens. So here we don't have causal self-attention. So here every token is taking attention from all of the previous and forward tokens. But when we're training neural network, we shouldn't be able to see forward tokens because then that would be easy to predict forward tokens if we see them. So, but it's not implemented here, but I'm telling you, we will learn this. So we will actually just, for each value, we will take context or do multiplications with just previous tokens. So that's going to be a short lesson on implementing attention in code. Let's learn to build and code a GPT-style LLM. So this is like ChatGPT. I recommend you watch these two previous lessons on attention mechanism explained and self-attention from scratch. So if you've seen transformer architecture, there are two parts, and this is good for sequence to sequence when you have encoder and decoder. So classic transformer architecture is good when you have like some sequence of words in one language, you want to translate that into different language. But GPT has only this part, only decoder, and that's good when you just want to keep generating text. And as it turns out, maybe this decoder-only transformer is also better for translation and sequence to sequence. So that's probably also, it works better in practice, even though the idea here is cool to have like two parts for two languages. But anyways, in our GPT architecture, we just have decoder, and we'll explain more what that is. We know that large language model will predict the next word. So if we have once upon a time, very far away there, it's gonna predict lived as the next likely word. So the four parts of transformer, we have causal masked multi-head self-attention, which is actually explained here in self-attention. We'll explain what multiple heads mean. And then add a normalization. So when you have input, you pass input token or tokens through self-attention. And after that's processed, you actually want to add same input and add this processed tokens with self-attention and add to the input that's not processed. So add them together. And when adding vectors, then neural network will actually, you give both information, both processed information and raw information for the neural network. So it has both of the information, and then it will use both. If you remove this residual connection that just adds unprocessed information, then neural network or language model will learn worse and slower, because these initial tokens also contain important information. So we don't just want to process and just have that, but also the initial. So you want to add those vectors. And this normalization, this can happen usually before self-attention, and it just to keep the vectors, the numbers, in a nice range between around 0 and 1 or -1, because big numbers or very small numbers can cause problems like gradient vanishing or gradient exploding. Because when you multiply numbers near 1, they're gonna stay, result is also gonna stay near 1. But if you multiply numbers like thousands and millions, the other numbers, next numbers, results will explode. And maybe such big numbers cannot be represented in computers. So we wanna keep our numbers around 1, 0. Feed-forward network, it's just a single multi-layer perceptron. So it takes as input this processed and normalized. So usually you would also put normalization before feed-forward and this mask before feed-forward. In the original transformer, it was after, but now we would put like before. So at the output of self-attention and the residual network, when we add those two, so this add and norm, so I guess norm would go before, but add would go after. So with that added vector result, we can normalize that again with this norm that we would put before feed forward, and then put that into feed forward. So that's input. Now we expand into the middle layer, hidden layer. It's gonna be like 4 times bigger usually than this input. And so in this middle layer of our feed forward network, there are a lot of facts like about basketball players, like all of the knowledge that neural network learned. It's like a data storage, and also it also transforms these tokens in different ways. So it has multiple purposes. And then in the hidden layer that's 4 times bigger than the token size in the input, it shrinks back to the token size at the output. And that's our one pass through the transformer. Now that can go back into attention, into the next pass, next layer, back again. And then we can repeat this cycle 10, 20, 30, maybe 60 times in big large language models. So we'll explain all of this again, don't worry. So these would be example hyperparameters here. So number of heads in self-attention. So we will just divide each token vector in self-attention into different parts, independent parts. And so we will then do attention on those independent parts, which are like independent key query value, independent key query value, all coming from the same token. But we're dividing them into multiple because now each head will learn different things. Maybe some head will learn to like do mathematics, some head will learn about medicine, etc. This is the dimension of the feed forward hidden layer that I was explaining that was 4 times bigger, and here it is 4 times bigger because the model is the token embedding size, and feed forward hidden dimension is 4 times bigger. Dropout, just to prevent overfitting. Vocab size, usually this is like 50,000 to 200,000 on big models. And this is the maximum context window sequence, like maximum of 512 tokens that you can have in your language model. And number of blocks can also be called number of layers. So how many times do we repeat this process? So self-attention norm, feed forward norm. So that's 1. Okay, then we go output here, we go back in, and then back in again. So 3 times in this case, 3 blocks or 3 layers. And these earlier layers will learn something, maybe to find out some basic features in text, and then later layers will learn maybe more complex things to generate next tokens, or to give information necessary to generate next tokens. Then we have rotary positional embeddings. This is how we encode which token comes after which token. This is the order of tokens. So is cat chasing the dog or dog chasing the cat? We use rope to encode the position of the words of the tokens. And let's go all the way down. This is where it happens. So we have our token, our vector embedding for the token, and we split it into 2. And the first, so we have x1 is the first half of the token, x2 is the second half of the token. And then we apply this rotation matrix. So rotation matrix is like a term in mathematics. When you have a vector, you can rotate the vector by multiplying it with this rotation matrix. So the idea here is that it's a bit more complex, but I'll explain. You want to rotate closer tokens or early tokens in the sentence maybe less, and later tokens in the sentence more. So the later the token, the more you want to rotate its vector. That's how, by this rotation, neural network will learn like the order of the tokens, how much, it will just see how much every token is rotated to understand their orders. And it's also good because it can also compare relatively tokens. So third token and fifth token, it can see that there is like two tokens in between relative to each other. So we don't need absolute positions like this is absolutely one, first, second, third. There is also a relative besides the absolute. So this rotation matrix, the matrix that rotates the tokens, can be expressed with sine and cosine. And this is how we can, this is one way to do it. So we multiply first half with cosine minus second half with sine. That's going to be our rotated x1. This is our first half now. And the second half, to get the new second half, we're going to rotate the original first half with sine plus second half with cosine. So that's going to be our new second half. And then we concatenate first and second half. And that's our new vector that now, token embedding, that now encodes positional information. And this code above is just how we generate this sine and cosine and how we decide how much for each position we should rotate, what the sine and cosine should be for each position. But this is a bit complex, so we'll leave this for another time. This is not so important now. This is a very good example here of the code. So this is in Andrei Karpaty's NanoChat, and apply rotary embeddings. We just get the x, our token embedding, cosine and sine, and we will split into x1 and x2 all of the x's. So x is like not just, in this case, it's not just one vector, it's all of the vectors. So we will split every vector in halves, and then we will apply the same rotation that I just explained, and then concatenate. This is the dimension, because now we don't just have one vector, we have like a whole batch of sequences of vectors. But the logic is same that I explained. Then let's look at some code in implementing causal self-attention with rope. We have a class, Causal Self-Attention, and that inherits from NN module. And we need to make sure that the token embedding is divided into number of heads without, like, it should be divisible by number of heads, because every head should have equal number of dimensions. And then head dimension will be just dividing the token dimension with number of heads. That's how many numbers or elements each head has. And then we have query key value. So in this case, we do all of the query key value in one go. So we go from D model to D model times 3, because D model is the token dimension. And our query key value will also be the token dimension, same size. And you can learn more about query key value in the previous videos, previous lessons about self-attention. So we want to generate 3 of them. We want to generate 3 query key value, and each has size of the token. So we need 3 times size the token. So we have a linear layer. It's like some learned network weights that's going to generate our key query and value. And we input the token, and we output 3 times the token size, which is going to be now different numbers. And so later we will just split this into 3, like take the first third as query, second third as key, last third as value. We also have output head. So after we combine all of the tokens, so after we do attention with tokens, this will just convert, because at the end of attention, we just added values from each attention, each token to the last one. We just added values. Now we need to convert from this mixed up value vector to the actual token embedding to exit attention mechanism. And keep in mind that in this case, value, key query value are same dimension as token, but it doesn't have to be. Actually, in big LLMs, key query value are smaller dimension. So at the end of attention mechanism, where we added all of the weighted values, we need to convert that mixed up value vector into the token embedding vector. And do that for every token if we are training, or just for one token if we are inferencing. But we'll talk about that more later. And we initialize rope here as well, pass in self-head dimension. In this case, this is how we defined it, so we need to pass in dimension of the head. And then, in this case, we want to get the batch size, how many independent conversations, sequence length, what is the maximum number of tokens in the sequence. And I guess we don't need the token dimension here. And so we generate key query values. So by just passing x through our linear layer that generates key query values, and then split. So this will get us like one big vector, 3 times model dimension. And then we split it into 3 parts for query key value. And then we need to split query key and value into heads. As I said, we will split query key value into heads, so each head will learn different things. Like maybe one will be about math or calculation or nouns or verbs. The other will do something else. So we will use query.view batch size sequence length that already exists, but that where previously was 1 dimension here, this was model dimension, now we split into 2 dimensions. So number of heads and head dimension. Number of heads and head dimension for each head. So now we do that for all of these. And we can apply rope, then to query and key. We don't need to apply rope for the value, just query and key. So next, in attention calculation, we want to do heads independently. So we will transpose this to put heads first. This is the batch size, and heads are independent dimensions. And then in every sequence length, we will do heads of the key query value. So sequence length is, for the sequence length, we will do same heads. So this is separating. Here we will separate them. Here we will also separate them here. But now here and here, they're together. They're grouped up by head. And so we do whole sequence length of the query key value together for this particular head and for the next head, etc. And then this is the formula for attention. And we talked about this formula in the previous lessons. This is how you do it. And then we want to apply mask so that every token in a sequence can only look at the previous tokens and not the future tokens. So it can only pay attention. So that this is during the training, by the way. So in inference, we don't need masks because we just have a sequence. We just do the next token once. We don't need to calculate every token with every other previous token in inference when we are generating, okay? But when we are training, we do need to calculate every token with every previous token to train better, to train on the whole thing. So this mask, again, will just make sure that tokens cannot look at, so query of the token cannot look at the keys of the following tokens because it's learning to predict those. So query can only look at the keys of the previous tokens for every token. And then we calculate softmax, which previously these scores are just numbers, logits. They don't add up to 1. They don't add up to 100%. So they can be like 2, 1, 0.5, whatever. And we need to make them add up to 100% because, let's take example this token. It needs to know how much to take of the information of context of every other previous token. So it's a lot easier to do that if you just have them add up to 100%. So it knows I should take 20% from this token, 20% of its value, 10% of this value, 5% of this value. So that's what softmax will do. It will just make the scores for every token, all of the scores with every other token add up to 100%. So it knows how much. And then we can drop out for ignore some of the scores to stabilize training to make it not so dependent on some particular scores or some particular positions. So this part, output, is where we perform the weighted sum of the values. So now this is where it takes context from every previous token based on the score, the importance. I explained here, V is the matrix of values for every token in the sequence. For example, V of the V of the cat, V of the set. So when we multiply attention scores and values, this is what it looks like. For example, output for the word set, it's gonna do 0.1 or 10% times value of the plus 0.6 times value of cat plus 0.3 times value of set. And usually you will see that these tokens usually take most of their own value. So maybe I should put 0.6 here and 0.6 there. So that's how we will get weighted sum of the values for each token of every previous token into that token. So that's how we do the context. And then after we do that, we need to now go back with the swapping heads and sequence length. So now we need to put sequence length after batch. And so we have sequence length, and then we will combine number of heads and head dimension to get model D, because now we want to transform from the query value space into the token space. So we will use this weight, so this output layer. So output is just it's our value space, and we pass that through this linear layer to get actual token space, token embedding. But before we pass our values, we need to convert them to the proper shape. So combine heads into one single vector. Then we have the transformer block where we combine all of that. So here we want to initialize feed forward, which we didn't make yet, by the way. So this is very simple. It goes from token embedding into the hidden 4 times bigger, and then go back to token embedding. And in this hidden 4 times bigger, you have all of the facts living there, all of the knowledge, and some ways to transform tokens as well. Because imagine attention as just collecting information into the token, last token, in order to predict the next token. And then this feed forward will process that information, mix it up, do something with it, create new insights. So I also have dropout between those expansion and contraction layers. So this is the whole formula. So we pass our token into first linear, use activation like ReLU, although this could be maybe SILU, SWIGLU, but let's now use ReLU. ReLU is simple and fast to compute. Then dropout to prevent overfitting, and then scale back into the token size. In our transformer block, we will initialize causal self-attention, feed forward, and then 2 normalizations. In this case, it's layer norm, but I should actually change this to RMS norm. RMS norm is just used more these days, and the dropout as well. And this is the forward of the transformer. Okay, so we pass in first through the attention. I guess we get input and mask here, although we could probably generate mask within attention as well. Passing through the attention and then normalize, although we could also put normalization before attention, but let's keep it this way now. And then feed forward, pass through, feed forward, normalize, and that's it. That's our transformer block. And then we have multiple of those blocks and output head and token, so we need to now combine everything into one. Here we need the entire vocabulary of tokens. So token embedding vocabulary will just be all of the tokens, vocab size, and each of the tokens has its own embedding. So vocab size times the model. Then we also define these list of blocks, of transformer blocks that I was just explaining. We will just do multiple. Number of blocks is gonna be 3 in our case, if you remember from the beginning of the video. And this is, I guess, final normalization that we get. And this is the output head that generates the next token. So this is after all of the blocks, after everything, output head will generate next token. And it has the model times walkup size. So it's basically gonna, for every token in the vocabulary, it will generate probability that this is the next token. So it converts our vector embedding from the transformer into set of probabilities, 50,000 probabilities if we have 50,000 tokens. It's just a linear layer. A vector token embedding into set of probabilities over entire vocabulary. So this can actually be huge, and you need some, so this can be 1/3 of the entire language model for small models. But there are some tricks. For example, Apple's cut cross attention. Maybe writing some kernels or GPU code. And let's see the forward pass through our GPT style decoder only transformer. We get our batch size, sequence length, the shapes. We get a device which will be GPU. We can create masks here, or we can do it in the attention. So this is how we create mask. As I said, I talked more about unsqueeze in my and torch ones and these PyTorch in my PyTorch fundamentals course in this school. So we just want to make sure that you have a triangular matrix where we have like a mask such that when we apply this to the attention for every single query, it will only have unmasked the previous keys, and it will have masked the following keys. So this mask will, for example, be for the first token, it will have all of the masks for the following tokens. It will just have one unmask for itself to pay the attention to itself, to do query and key of itself. For the second token, it will have unmasked itself and previous token, but masked all of the next tokens. Third token will have first 3. So you see how you have 1, 2, 3, 4. So it's like a triangle of masks. And this triangle here is also masked. And this is unmasked. So that's why we need this triangular matrix. And in the future, maybe we will talk more about this as well. Then we will pass all of our tokens through our token embedding layer to replace all of the tokens with their embeddings. So this will give us like list of embeddings instead of the list of tokens. And this is good for stabilization, dividing these tokens with the square root, these embeddings with the square root of the model dimension. As I said, you want to keep like your numbers around 1, around 0. So that's what this will do. It will push them towards 1. Then we pass our x through our blocks. So 4 block in self blocks. So we have 3 blocks. We pass x through every transformer block. And what block includes attention and feed forward. So we do that 3 times here in this loop. And then we normalize at the end and generate the probability over all of the possible tokens to be the next token. But these are logits, these are not probabilities, these are just like numbers. So we can later turn them into probabilities with softmax. But basically these logits are also like numbers. Higher number means like it will later become higher probability for this token to be chosen. Okay, and then this is how we use and train this GPT. So we initialize it. We select the device, which is going to be CUDA, which means GPU, NVIDIA GPU, if it's available. You better not train on CPU, that's not going to be fun, it's going to be so long. And then put the model 2 device to GPU, so because you initialize it here, it can be initialized on CPU, you want to move it to GPU. And then we can have like this some dummy data. So this source, it's just gonna be our random tokens, example tokens. So this is, let's say we have like some text here, but it's now randomly generated, some tokens, some sequences and stuff. And this is for the model training. We need cross entropy loss to check the model's prediction versus the real next token. And we will use Adam to update weights to make the model learn based on this loss to next time generate better loss. And loss in large language models should be around 1 to 2 to 3. If you have 0.001 or 10, your loss, then there is some bug. I had 0.001 loss because I had some bug. And then I discovered it. And so loss should be around 1 to 3. And then model.train, this will train because we are inheriting all of these like train and stuff from PyTorch. This is done by PyTorch. So this is how you train large language model. You have a sequence. So your inputs are gonna be entire sequence except the last token. And your target is gonna be entire sequence except the first token. And I'll explain why, but you see here, we take all of the batches, all of the conversations, all of the sequences, I should say. And everything, inputs is everything except last, and target is everything except the first token. So from first, so index 0, token 0 is not, because here in the inputs, we will start with just one token, and we want to predict the next token. So the target cannot be the first token, because we can start from the first. We cannot start from like nothing in large. So we're not training model to start from nothing. We are training the model to start from at least one token. So that's why target cannot be that first token. Okay? And inputs will go until last, but not last, because during the training, we can have, it's possible to have all of the tokens, all of the sequence as inputs except last when we are predicting the last. Okay, so all of these combinations are possible. So you can have like half of the tokens given, and you need to predict the next half. Or you need to, okay, so you wouldn't predict, you would just predict the next token. So let me simplify. All of the possible combinations when training large language model are, you can have one token and predict next. You can have two tokens predict next. You can have three tokens until you have almost all and predict the last. So that's why inputs can be from 0 until last but not last. And targets can be from the second token until last. So all of the possible combinations where you have at least one to predict the next, or until all except last to predict last. So as I said, we will get logits like numbers when we pass this through the model. And so in this case, it looks like we're not using softmax. That's okay too. To put them into percentages, we can also calculate loss by just comparing the current logits to the target tokens. So the highest logit should be same as the target, the correct token. And if it's not, then we calculate the loss, update weights, do optimization steps. So we empty out gradients from the last backpropagation. You calculate all of the chain rule, the gradients, and then you update weights to reduce the loss. So that's gonna be it for our GPT style transformer. I'm gonna put this video here and see you in the next lesson.